What if I told you that in less than a decade, a mountain of rock and metal bigger than the Eiffel Tower will sweep past Earth, closer than the satellites we rely on every single day? Not some distant comet, not a passing piece of space fluff, but a genuine chunk of the cosmos that will thread the needle between us and our fragile layer of technology floating overhead. It sounds like the premise of a disaster movie, but it's not fiction. The date is already circled in red on the calendars of every astronomer on the planet. April 13, 2029. A Friday. A Friday the 13th. Now, here's the stranger part. The world's attention isn't on this asteroid. Instead, the headlines are captured by another visitor. A mysterious comet arriving from interstellar space, a rare tourist with a glowing tail and a poetic name, 3i Atlas. The media has branded it an alien messenger. A cosmic outsider. A beautiful wanderer. But here's the twist. That alien visitor will stay hundreds of millions of kilometers away, too far to ever matter. Meanwhile, a far more dangerous neighbor is quietly moving in, one that will pass so close you could see it with your naked eye. So what exactly are we looking at here? That's the central question. Why are we obsessed with the harmless tourist, while ignoring the actual neighbor that could, in theory, end our civilization? To answer that, we need to start with the visitor that everyone is talking about. A streak of light beyond Mars, trailing a veil of ice and dust, the comet officially designated 3i Atlas. It's only the third interstellar object ever confirmed in human history. Before this, we had Oumuamua in 2017, a cigar-shaped rock that slipped past the sun so quickly we barely caught a glimpse. Then came Borisov in 2019, a more classic comet, a dirty snowball with a tail. And now, Atlas, drifting in from the cold between the stars. These things are like cosmic hitchhikers. They don't belong to our solar system. They're on hyperbolic trajectories, which means they pass once and then vanish forever, like a one-night stand with the sun. And that's exactly why the press can't get enough of them. They're exotic. They're mysterious. They invite speculation. Every article seems to whisper the same unspoken question: could this be proof of alien life? Could these interstellar fragments carry organic compounds from distant worlds? Could they be seeds drifting across the galaxy, waiting for a planet like ours to take root? The imagination runs wild. And the photographs don't hurt either. The Hubble telescope captures a glowing teardrop of dust, the James Webb teases out spectral fingerprints of strange molecules. It looks beautiful. It feels important. But here's the thing. Atlas is harmless. Its closest approach to Earth will be nearly 270 million kilometers away. That's so far the Moon could fit into the gap nearly 700 times. By the cold math of orbital mechanics, Atlas could never hurt us. It's a firework in the distance. Lovely to watch. Scientifically valuable, yes. But completely irrelevant to planetary defense. And yet, while we're staring at this harmless spectacle, something else is creeping in. Something closer. Something far less glamorous but infinitely more important. An asteroid named Apophis. Officially catalogued as 99942 Apophis, after the Egyptian god of chaos. Let's pause here. Imagine standing outside on a warm April night in 2029. You look up, and you see a moving star, bright enough to catch with your own eyes, racing across the heavens. That's Apophis. No telescope required. It will skim past Earth at a distance of only 31,000 kilometers. To put that into perspective, our geostationary satellites orbit at 35,786 kilometers. Apophis will fly underneath them. Closer than our technology. Closer than anything of its size has come in recorded history. So why isn't this the headline? Why aren't we plastering the name Apophis across every news outlet? Because it isn't exotic enough. It isn't mysterious enough. It doesn't sound like science fiction. And that's the danger. See, the real threats aren't the flashy tourists from other star systems. The real threats are our neighbors. The near-Earth asteroids. Objects that share our orbit around the Sun, quietly circling with us, sometimes passing close enough to graze our atmosphere. These are the cousins of the rock that wiped out the dinosaurs 66 million years ago. The brothers of the meteor that flattened 2,000 square kilometers of Siberian forest in 1908. The uncles of the 20-meter fragment that exploded over Chelyabinsk in 2013, injuring more than 1,500 people just by its shockwave. Apophis belongs to this family. Not exotic. Not alien. Just ordinary rock and metal. And yet, it is precisely the ordinary ones that matter. Because they don't vanish after one pass. They come back. Again and again. Their orbits can shift, pulled by Jupiter's gravity, nudged by the Yarkovsky effect, tiny forces caused by heat re-radiating into space. Over decades, those nudges can turn a safe orbit into a dangerous one. That's the paradox. The exotic visitors capture our imagination, but they're harmless. The ordinary neighbors bore us, but they're deadly. And so tonight, as we begin this journey, we're going to reframe the story. We're going to shift our gaze from the glittering comet that poses no threat, to the dull, rocky asteroid that might. Because planetary defense isn't about spectacle. It's about probability. It's about what actually comes close. Let's zoom out for a moment. Picture the solar system as a giant racetrack. The planets are cars locked into their lanes, circling the track over and over. Now imagine marbles scattered across that track. Some marbles roll harmlessly between lanes. Others cross paths with the cars. Most of the time, the cars miss them. But every once in a while, the timing is wrong. And when that happens, you get a collision. That's what near-Earth asteroids are, cosmic marbles crossing our track. Atlas, the interstellar comet, is not on the track. It just shoots across the stadium once and vanishes. It makes a pretty streak in the sky, but it never threatens the cars. Apophis, on the other hand, is one of those marbles rolling along the lanes, circling the same track we are. It's part of our race. And that makes it dangerous. This is the story most people don't hear. Not because astronomers don't care, they care deeply, but because the media isn't built to sell stories about boring rocks. The truth is, hundreds of near-Earth asteroids pass closer than the Moon every single year. Most are small, too small to survive the atmosphere. But some are not. And every now and then, we discover a big one. One like Apophis. One that makes even the professionals nervous. So why aren't we panicking? Why aren't we bracing for impact? Because Apophis will miss. At least this time. NASA has calculated its trajectory with exquisite precision. The numbers say it will fly past harmlessly in 2029. But that's not the end of the story. Not even close. Because there are things about Apophis, and about asteroids in general, that we don't fully understand. And that's where this journey really begins. Because the question isn't whether Apophis will hit us in 2029. It won't. The question is what happens after. Where will it go? What forces will nudge its orbit in the decades that follow? Could it find a gravitational keyhole, a tiny region of space that bends its path just right to set up a future collision? That's the puzzle. That's the real cliffhanger. What if I told you that in less than a decade, a mountain of rock and metal bigger than the Eiffel Tower will sweep past Earth, closer than the satellites we rely on every single day? Not some distant comet, not a passing piece of space fluff, but a genuine chunk of the cosmos that will thread the needle between us and our fragile layer of technology floating overhead. It sounds like the premise of a disaster movie, but it's not fiction. The date is already circled in red on the calendars of every astronomer on the planet. April 13, 2029. A Friday. A Friday the 13th. Now, here's the stranger part. The world's attention isn't on this asteroid. Instead, the headlines are captured by another visitor. A mysterious comet arriving from interstellar space, a rare tourist with a glowing tail and a poetic name, Three-Eye Atlas. The media has branded it an alien messenger. A cosmic outsider. A beautiful wanderer. But here's the twist. That alien visitor will stay hundreds of millions of kilometers away, too far to ever matter. Meanwhile, a far more dangerous neighbor is quietly moving in, one that will pass so close you could see it with your naked eye. So what exactly are we looking at here? That's the central question. Why are we obsessed with the harmless tourist, while ignoring the actual neighbor that could, in theory, end our civilization? To answer that, we need to start with the visitor that everyone is talking about. A streak of light beyond Mars, trailing a veil of ice and dust, the comet officially designated Three-Eye Atlas. It's only the third interstellar object ever confirmed in human history. Before this, we had Oumuamua in 2017, a cigar-shaped rock that slipped past the sun so quickly we barely caught a glimpse. Then came Borisov in 2019, a more classic comet, a dirty snowball with a tail. And now, Atlas, drifting in from the cold between the stars. These things are like cosmic hitchhikers. They don't belong to our solar system. They're on hyperbolic trajectories, which means they pass once and then vanish forever, like a one-night stand with the sun. And that's exactly why the press can't get enough of them. They're exotic. They're mysterious. They invite speculation. Every article seems to whisper the same unspoken question: could this be proof of alien life? Could these interstellar fragments carry organic compounds from distant worlds? Could they be seeds drifting across the galaxy, waiting for a planet like ours to take root? The imagination runs wild. And the photographs don't hurt either. The Hubble telescope captures a glowing teardrop of dust, the James Webb teases out spectral fingerprints of strange molecules. It looks beautiful. It feels important. But here's the thing. Atlas is harmless. Its closest approach to Earth will be nearly 270 million kilometers away. That's so far the Moon could fit into the gap nearly 700 times. By the cold math of orbital mechanics, Atlas could never hurt us. It's a firework in the distance. Lovely to watch. Scientifically valuable, yes. But completely irrelevant to planetary defense. And yet, while we're staring at this harmless spectacle, something else is creeping in. Something closer. Something far less glamorous but infinitely more important. An asteroid named Apophis. Officially catalogued as 99942 Apophis, after the Egyptian god of chaos. Let's pause here. Imagine standing outside on a warm April night in 2029. You look up, and you see a moving star, bright enough to catch with your own eyes, racing across the heavens. That's Apophis. No telescope required. It will skim past Earth at a distance of only 31,000 kilometers. To put that into perspective, our geostationary satellites orbit at 35,786 kilometers. Apophis will fly underneath them. Closer than our technology. Closer than anything of its size has come in recorded history. So why isn't this the headline? Why aren't we plastering the name Apophis across every news outlet? Because it isn't exotic enough. It isn't mysterious enough. It doesn't sound like science fiction. And that's the danger. See, the real threats aren't the flashy tourists from other star systems. The real threats are our neighbors. The near-Earth asteroids. Objects that share our orbit around the Sun, quietly circling with us, sometimes passing close enough to graze our atmosphere. These are the cousins of the rock that wiped out the dinosaurs 66 million years ago. The brothers of the meteor that flattened 2,000 square kilometers of Siberian forest in 1908. The uncles of the 20-meter fragment that exploded over Chelyabinsk in 2013, injuring more than 1,500 people just by its shockwave. Apophis belongs to this family. Not exotic. Not alien. Just ordinary rock and metal. And yet, it is precisely the ordinary ones that matter. Because they don't vanish after one pass. They come back. Again and again. Their orbits can shift, pulled by Jupiter's gravity, nudged by the Yarkovsky effect, tiny forces caused by heat re-radiating into space. Over decades, those nudges can turn a safe orbit into a dangerous one. That's the paradox. The exotic visitors capture our imagination, but they're harmless. The ordinary neighbors bore us, but they're deadly. And so tonight, as we begin this journey, we're going to reframe the story. We're going to shift our gaze from the glittering comet that poses no threat, to the dull, rocky asteroid that might. Because planetary defense isn't about spectacle. It's about probability. It's about what actually comes close. Let's zoom out for a moment. Picture the solar system as a giant racetrack. The planets are cars locked into their lanes, circling the track over and over. Now imagine marbles scattered across that track. Some marbles roll harmlessly between lanes. Others cross paths with the cars. Most of the time, the cars miss them. But every once in a while, the timing is wrong. And when that happens, you get a collision. That's what near-Earth asteroids are, cosmic marbles crossing our track. Atlas, the interstellar comet, is not on the track. It just shoots across the stadium once and vanishes. It makes a pretty streak in the sky, but it never threatens the cars. Apophis, on the other hand, is one of those marbles rolling along the lanes, circling the same track we are. It's part of our race. And that makes it dangerous. This is the story most people don't hear. Not because astronomers don't care, they care deeply, but because the media isn't built to sell stories about boring rocks. The truth is, hundreds of near-Earth asteroids pass closer than the moon every single year. Most are small, too small to survive the atmosphere. But some are not. And every now and then, we discover a big one. One like Apophis. One that makes even the professionals nervous. So why aren't we panicking? Why aren't we bracing for impact? Because Apophis will miss. At least this time. NASA has calculated its trajectory with exquisite precision. The numbers say it will fly past harmlessly in 2029. But that's not the end of the story. Not even close. Because there are things about Apophis, and about asteroids in general, that we don't fully understand. And that's where this journey really begins. Because the question isn't whether Apophis will hit us in 2029. It won't. The question is what happens after. Where will it go? What forces will nudge its orbit in the decades that follow? Could it find a gravitational keyhole, a tiny region of space that bends its path just right to set up a future collision? That's the puzzle. That's the real cliffhanger. We'll get to that. But for now, let's remember the irony. While the world gazed at a harmless comet from another star, the real story was unfolding closer to home. A gray, ordinary asteroid named after the god of chaos, creeping silently toward the closest pass in human history. And the strangest part is, that close call might actually be a gift. Because when Apophis schemes past us in 2029, we'll have the chance to watch it up close. To study it with ground-based telescopes, with radar, even with spacecraft. We'll see how Earth's gravity tugs at it, maybe even reshapes it. And in that process, we'll learn lessons that could one day save our civilization. But before we get to the science, before we see how Apophis turned from nightmare to opportunity, we need to walk back in time. To the night of its discovery. To the moment when astronomers realized they might have just spotted humanity's most precisely predicted doomsday. And that moment changed everything. June 19, 2004. A quiet evening at the Kitt Peak National Observatory in Arizona. 3 astronomers, Roy Tucker, David Tholen, and Fabrizio Bernardi, were conducting what seemed like routine work. They were scanning the skies for faint points of light, part of the ongoing search for near-Earth asteroids. Most nights, their images revealed nothing remarkable. Just stars, galaxies, maybe a faint asteroid moving predictably against the backdrop of space. But that night, their cameras captured something different. A dot of light that moved just enough between exposures to suggest an object in Earth's neighborhood. At first, it seemed ordinary, another small asteroid to be catalogued and forgotten. They logged it with a temporary designation, 2004 MN4. But the data didn't stay ordinary for long. Within days, as more observations came in, computers at NASA's Jet Propulsion Laboratory began calculating the orbit. The results made scientists pause. The trajectory suggested a possible intersection with Earth in the year 2029. Not just a close pass, but an actual collision course. The probability at first looked small, but then it climbed. With every new observation, the calculations grew more concerning. By December 2004, Apophis, as it would soon be named, carried an estimated 2.7% chance of hitting Earth on April 13, 2029. That might sound tiny, but in the world of asteroid predictions, it was enormous. Imagine betting on a lottery where your odds suddenly improved to 1 in 37. That's how alarming this was. For comparison, the chance of being struck by lightning in your lifetime is about 1 in 15,000. Apophis, at that moment, looked hundreds of times more likely to hit Earth than lightning was to hit you personally. This wasn't science fiction anymore. This was math. Cold orbital mechanics. And so the panic began. Scientists scrambled to gather more data. Telescopes across the world pointed at the faint rock whenever possible, measuring its position against background stars, feeding new numbers into orbital models. But for months, the uncertainty remained. The media caught on slowly at first. But once the word collision entered the conversation, headlines exploded. Asteroid could hit Earth in 2029. Scientists warn of global catastrophe. The date made it irresistible, Friday the 13th. An asteroid named after the Egyptian god of chaos, threatening to strike on the unluckiest day of the calendar. It felt almost scripted. But what exactly were we facing? Apophis wasn't a small rock. Radar observations revealed it to be around 340 meters long, with a width of about 150 meters. For scale, that's bigger than 3 football fields laid end to end. A rock that size, traveling at cosmic speeds, carries energy equivalent to several hundred megatons of TNT. More than 10 times the power of the largest nuclear weapon ever tested. No, it wouldn't wipe out all life on Earth like the dinosaur killer Chicxulub impact 66 million years ago. But it could devastate a continent. If it struck land, it would leave a crater several kilometers wide, vaporize everything at ground zero, and trigger shockwaves flattening cities within 50 kilometers. If it struck the ocean, it could launch tsunamis hundreds of feet tall across coastlines. Millions could die. Billions could feel the aftershocks through disrupted food supplies and climate shifts. This wasn't an extinction event. But it was civilization-level danger. And for the first time in history, we had a date. A real, specific day on the calendar when the chaos god might descend. Scientists rated Apophis a 4 on the Torino scale, the highest ever given at the time. For context, the Torino scale runs from 0 to 10. 0 means no chance of impact. 10 means certain global catastrophe. 4 sits in the yellow zone. Not doomsday, but not ignorable either. Meriting attention by astronomers was the official language. Unofficially, it was enough to make the astronomy community sweat. The fear wasn't just about 2029. The real complication was what astronomers call gravitational keyholes. Imagine a cosmic bullseye, a tiny zone in space. If Apophis passed through that zone during its 2029 flyby, Earth's gravity would tug on it just enough to alter its orbit, setting it up for a collision on a later pass, most worryingly, in 2036. These keyholes are small. Sometimes just a few hundred meters wide. But in the vastness of space, threading one of them can make the difference between a harmless pass and an eventual direct hit. And back in 2004, astronomers couldn't rule that out. The situation was unprecedented. Never before had humanity identified a specific asteroid with such a high impact probability, tied to such a specific date. The science was uncertain, the public was anxious, and the clock was ticking. NASA's Near-Earth Object Program jumped into overdrive. Observatories worldwide joined the campaign. Every night of observation shrank the uncertainties, refining the models. Slowly, the numbers shifted. The odds of a 2029 collision began to fall. By mid-2005, the probability dropped from 2.7% to effectively zero. The relief was palpable. Apophis would not strike in 2029. Instead, it would skim past Earth, closer than our satellites, but miss us entirely. Humanity dodged the bullet. At least this time. Yet even with the 2029 threat eliminated, the 2036 keyhole remained a concern. For years afterward, Apophis lingered as a symbol of planetary vulnerability. Every time it came back into view, astronomers checked again, refining its path, updating predictions. Eventually, the discovery of a subtle effect, the Yarkovsky effect, caused by heat radiating unevenly from its surface, allowed scientists to rule out even the 2036 possibility. Apophis was cleared of immediate danger. Earth was safe, at least for the next century. But the lesson stuck. Apophis proved just how fragile our certainty can be in the early days of an asteroid's discovery. At first, we don't know enough. Our measurements are too limited. The uncertainties are wide. And in that fog of data, scary probabilities can appear. Only by tracking the object longer, sometimes for years, can we shrink the uncertainty and find the truth. That's why Apophis matters. It wasn't just a close call. It was a dress rehearsal. It forced humanity to admit that we live in a cosmic shooting gallery, and that someday, another object might not miss. The night of discovery in 2004 was the moment the god of chaos reminded us that the universe doesn't care about our calendars. A faint dot on a CCD camera became the most precisely predicted doomsday in human history. And even though it was later dismissed, the fear was real. The wake-up call was real. And as we'll see, that wake-up call transformed planetary defense from a fringe curiosity into a serious global effort. Because when you realize a 340-meter rock can nearly end up on your doorstep, you don't shrug and move on. You start building walls. But the real twist in the Apophis story is this: what began as a symbol of destruction eventually became an opportunity. A chance to test our science. To probe asteroid behavior. To learn how to defend ourselves. And that transformation, from chaos to knowledge, is what makes 2029 more than just a close pass. Because the asteroid might miss us. But it won't leave unchanged. By early 2006, the panic had cooled. The data was in. The dreaded 2029 impact had been ruled out. The asteroid would pass close, frighteningly close, but not collide. Astronomers breathed easier. Newspapers moved on. The public, once captivated by headlines of doomsday, quickly forgot. But the scientists didn't forget. They couldn't. Apophis wasn't just a rock. It was a case study in how planetary defense works, or doesn't. And it became the pivot point where humanity's relationship with asteroids began to change. At first, Apophis was a name whispered in worried tones. Level 4 on the Torino scale, the highest ever assigned. A 3% chance of impact. But once the impact probabilities fell to zero, Apophis became something else entirely. It became an opportunity. Why? Because no asteroid of comparable size had ever been observed making such a close approach in modern history. On April 13, 2029, Apophis will pass Earth at just 31,000 kilometers, closer than our geostationary satellites. For context, that's like a bullet missing your ear by the width of a hair. From the standpoint of celestial mechanics, it's astonishingly near. From the standpoint of science, it's a gold mine. When objects pass that close, Earth's gravity doesn't just bend their path. It squeezes them, pulls on them, shakes them. These tidal forces can stretch and compress asteroids in ways we rarely get to observe. Apophis, as it schemes by, could reveal secrets about asteroid interiors that no spacecraft has ever captured. Because here's a little-known fact. Most asteroids aren't solid boulders. They're rubble piles, loose collections of rock, gravel, and dust, barely held together by their own weak gravity. Think of a bag of marbles, shaken but not sealed. Or a mound of sand just solid enough to keep its shape. These rubble piles behave very differently from solid rock. A spacecraft crashing into one might splash material into space. A gravitational tug might shift its orbit more easily than expected. Understanding how rubble piles respond to stress is critical for designing deflection strategies. And Apophis will give us the ultimate natural experiment. When it passes Earth in 2029, our planet's gravity will exert a force about 50 times stronger than the asteroid's own self-gravity. That could trigger landslides on its surface. It could jostle boulders. It could even alter its rotation. Observers will watch to see whether Apophis spins faster or slower, whether new scars appear on its face, whether dust clouds are kicked into space. In essence, Earth will become a giant laboratory, reshaping the asteroid right in front of our eyes. This is why scientists no longer talk about Apophis as only a threat. They talk about it as a once-in-a-lifetime opportunity. For months leading up to the flyby, telescopes across the globe will track it. During the closest approach, radio radar stations will map its surface in exquisite detail, perhaps down to meter-scale resolution. Amateur astronomers will contribute too, recording its brightness changes, its motion across the stars, its naked-eye spectacle. Everyone, from backyard stargazers to NASA scientists, will be part of the show. And here's the poetic twist. The very asteroid that once symbolized chaos has become our best teacher in planetary defense. By studying Apophis, we'll learn how to deal with the next threat. The next rock that doesn't miss. NASA, of course, didn't want to waste the chance. They had just completed the OSIRIS-RX mission, which visited another asteroid, Bennu, and brought back samples to Earth in 2023. Instead of retiring the spacecraft, NASA repurposed it. Renamed OSIRIS-APEX, it was set on a new course to rendezvous with Apophis shortly after its 2029 flyby. That means humanity will not only watch from Earth but also send a robotic emissary to orbit the chaos god itself, measuring the aftermath of its encounter with our planet. This mission is historic. For the first time, we'll see an asteroid before and after a major gravitational flyby. It's like a before and after photo shoot, only the model is a 340-meter-long rock, and the photographer is a billion-dollar spacecraft. The science return could be extraordinary. We'll learn how Apophis's orbit changes. How its surface shifts. How its interior responds to stress. These insights will go directly into the models used to design deflection strategies for future asteroids. Because make no mistake, Apophis is not the last. There are tens of thousands of near-Earth objects out there. We've catalogued about 34,000 so far. But there are many more waiting to be found, especially the smaller but still dangerous ones in the 100 to 500 meter range. Apophis is simply the one that came close enough to grab our attention. And attention matters. Before Apophis, planetary defense was almost an afterthought. NASA tracked asteroids, yes, but funding was meager, coordination was limited. After Apophis, everything accelerated. Governments began to recognize the risk. The Planetary Defense Coordination Office was formalized. The European Space Agency expanded its Space Situational Awareness Program. International cooperation grew. Apophis wasn't just a rock. It was a catalyst. Of course, the story isn't entirely one of reassurance. Even though we've ruled out a 2029 impact, Apophis is still a potentially hazardous asteroid. Its orbit intersects Earth's. Its size is significant. And while we can project its path with high confidence for the next century, beyond that, uncertainty grows. Gravity is subtle. Small forces like the Yarkovsky effect, the recoil from sunlight warming its surface, can nudge its orbit by meters each year. Over decades and centuries, those nudges add up. One day, far in the future, Apophis, or one of its cousins, could still find its way onto a collision course. That's why 2029 matters so much. It's not just a spectacle. It's a trial run. A dress rehearsal for the day when the asteroid doesn't miss. And whether we admit it or not, that day will come. It might be in 100 years. It might be in 1,000. But cosmic history guarantees it. Earth has been hit before. Earth will be hit again. Which brings us to an uncomfortable truth. We've spent centuries marveling at the beauty of comets, telling stories about gods and dragons in the sky, dreaming about alien visitors from the stars. But the real danger, the real test of our survival as a species, lies not in the spectacular but in the ordinary. The dull gray rocks that lurk in the darkness, unnoticed until it's almost too late. Apophis is our wake-up call. And how we respond to that call could determine whether our great-great-grandchildren look up at the night sky with wonder, or not at all. So, yes. In 2004, Apophis was a scare. By 2006, it became a relief. But in 2029, it transforms again, into a once-in-a-lifetime classroom. Earth's gravity will teach us how asteroids behave. Our telescopes will capture every detail. Our spacecraft will watch from up close. The chaos god, once feared, is now our teacher. But make no mistake, lessons from chaos are never gentle. And that's why the most important part of the Apophis story isn't the near miss in 2029. It's what that near miss reveals about our place in the cosmos. Because the question isn't whether Earth will be struck again. The question is when. And the asteroid that finally finds us might not be as generous as Apophis. But before we jump to the future, we need to step back once more. To understand how we even know what Apophis is made of. How astronomers measure its shape, its spin, its reflectivity. And why those details aren't trivia but life or death information. Because the more you know about a rock, the better chance you have to move it. To understand why Apophis matters, you first have to know what it is. Not in mythological terms, but in physical ones. Because planetary defense is not a movie where you just fire a missile at the sky and watch fireworks. It's engineering. It's physics. And the details, down to the spin of a rock and the way its surface heats up in sunlight, determine everything about whether we can protect ourselves. So what do we know about Apophis? Radar studies from facilities like Arecibo, before its tragic collapse in 2020, and NASA's Goldstone Deep Space Communications Complex gave us some of the first clear pictures. Not photographs exactly, but radar reflections that revealed its size and shape. What emerged was sobering, a peanut-shaped asteroid about 340 meters long and 150 meters wide. Large enough to destroy a region. Not large enough to kill the planet. In other words, a city killer. Its surface reflects only about 23% of the sunlight that strikes it. That makes it relatively dark, harder to spot against the backdrop of stars. Its composition appears to be stony, with silicate rock mixed with nickel and iron. That puts it in the category of S-type asteroids, one of the most common families in the inner solar system. Not exotic. Not rare. Ordinary, in fact. And that ordinariness is exactly what makes it dangerous. But the devil is in the details. Scientists need to know its density. Is it a solid monolith, or a rubble pile held together by gravity? That changes everything. A kinetic impactor, essentially slamming a spacecraft into it, would behave very differently against a solid chunk of rock than against a loose collection of gravel. A rubble pile might absorb the blow like a sponge, ejecting material and multiplying the effect. A monolith might barely budge. They also need to know its spin. Apophis rotates once every 30.6 hours, a leisurely tumble compared to many smaller asteroids. But that rotation could change when it passes Earth in 2029. Earth's gravity might speed it up or slow it down, depending on how the forces act on its elongated body. If the rotation changes, the Yarkovsky effect, the subtle push from heat re-radiating into space, changes too. That alters its orbit in ways that add up over decades. And then there's its internal structure. We don't know for sure whether Apophis is mostly solid, mostly porous, or somewhere in between. The only way to know is to watch how it reacts to stress, exactly what Earth's tidal forces will provide in 2029. Every landslide, every shift in spin, every wobble will tell us something about how asteroids like Apophis are built. This is why planetary defense experts get excited about details that sound trivial to the public. Because if an asteroid is ever truly headed our way, those details will decide whether humanity survives. Think about it like this. Suppose you need to stop a truck rolling downhill. Do you tie a rope to it? Do you push it sideways? Do you try to smash into it with another vehicle? The answer depends entirely on whether it's a solid steel truck, a truck filled with sand, or a truck carrying loose gravel. The weight, the structure, the distribution of mass, all of it changes the best way to act. The same is true for asteroids. This detective work has already paid off in the past. Take Bennu, the asteroid visited by NASA's OSIRIS-Rx mission. Before the spacecraft arrived, scientists thought Bennu's surface would be relatively smooth. Instead, it turned out to be a nightmare of jagged boulders and loose rubble. When OSIRIS-Rx touched down to collect a sample, it sank far deeper into the surface than anyone expected, as though landing in a ball pit. The lesson? Our assumptions can be wrong. And if you were trying to deflect Bennu instead of sample it, those wrong assumptions could mean disaster. Apophis offers the same kind of reality check. By studying it in detail, we calibrate our expectations. We replace guesswork with data. And that data may one day be the difference between moving a rock safely away from Earth, or watching helplessly as it slams into us. But Apophis also teaches us something else, something more unsettling. Even when we think we know an asteroid, small forces can change the story. Enter the Yarkovsky effect. Named after a 19th-century Russian engineer, this effect is one of the strangest, most subtle phenomena in orbital mechanics. It works like this: sunlight hits an asteroid, warming its surface. As the asteroid rotates, that surface later radiates heat back into space. But the radiation isn't perfectly symmetrical. It's like a tiny thruster firing over and over again. Over years and decades, that microscopic push can shift the asteroid's orbit by kilometers. For small asteroids, the Yarkovsky effect can be dramatic. For larger ones like Apophis, it's still enough to matter. It was only in 2021 that astronomers finally measured this effect precisely for Apophis, confirming it was drifting slightly away from its purely gravitational path. That measurement allowed them to rule out a collision in 2036, closing the book on one of the scariest scenarios. But here's the sobering truth. If we hadn't measured it, we wouldn't know. The margin of error would have left the door open to catastrophe. And that's the bigger lesson. Asteroid defense requires patience. Years of measurements. Decades of tracking. Because only with that patience can we separate phantom threats from real ones. Which brings us back to the illusion of safety. Yes, Apophis is safe for the next century. NASA says so. The math agrees. But it's safe because we've measured it. Safe because we've studied it. Safe because we've done the work. If we hadn't, it would still loom over us as a mystery, a possible doomsday lurking in the shadows. And if Apophis can be measured, so can others. The problem is scale. There are tens of thousands of asteroids we haven't catalogued yet. Many are small, but still large enough to devastate a city if they struck. They're out there, slipping through the dark, waiting to be discovered. Every month, astronomers add new ones to the list. Every year, they refine their orbits. But the job is far from done. Apophis, in that sense, is both a relief and a warning. A relief, because we know it will miss. A warning, because it shows how easily we could be surprised. Without careful tracking, without relentless observation, the chaos god might still be haunting our future. So here's the paradox. Apophis is ordinary. A stony S-type asteroid. Common as dust. And yet, its ordinariness is exactly why it matters. Because it represents the category of object most likely to hit us one day. Not the flashy interstellar visitor. Not the spectacular comet. Just the quiet neighbor that crosses our path, again and again, until one day, the geometry lines up wrong. The astronomers who first spotted it in 2004 understood that in their bones. That's why the fear was real. That's why the wake-up call echoed. And that's why 2029 is not just a spectacle but a moment of truth. When Apophis passes Earth on that April night, millions will look up and see it moving across the stars. But astronomers will see something more. They'll see data. They'll see answers to the questions that have haunted planetary defense for decades. They'll see the chaos god stripped bare by gravity, forced to reveal its secrets. And those secrets could one day be the difference between survival and extinction. But before we get there, let's step into the world of probability. Because when you strip away the drama, asteroid danger comes down to a formula. Size times proximity times probability. And the way those numbers play out tells us something unsettling about our place in the cosmos. And that is the story we'll dive into next. When most people think about asteroid danger, they picture Hollywood. They imagine a giant fireball streaking across the sky, explosions, chaos, the end of everything. What they don't picture is math. Cold, statistical math. But that's where the real story lives. Because planetary defense is not about drama, it's about probabilities. And probabilities, if you're paying attention, can be far more chilling than a special effects reel. Let's start with the basics. To evaluate asteroid risk, astronomers combine three numbers: size, distance, and probability. Each on its own means little. Put them together, and you get a picture of whether we should lose sleep. Size first. Not every asteroid is worth worrying about. A rock the size of a car burns up in the atmosphere, producing nothing more than a spectacular fireball. But once you get to about 20 meters across, like the Chelyabinsk meteor in 2013, you have real damage potential. That one shattered windows across an entire city, injuring over 1,500 people with flying glass. Scale that up to 50 meters, and you're talking about flattening a city. At 140 meters, the threshold for potentially hazardous asteroid, the destruction reaches regional levels. Hundreds of kilometers could be devastated. And once you cross 300 meters, like Apophis, you're staring at the possibility of continental-scale catastrophe. Distance next. Space is vast, so close has a different meaning. An asteroid passing 10 million kilometers away might sound terrifying, but it's actually routine. Thousands do so every year. The moon is 384,000 kilometers away. When something passes within lunar distance, astronomers start to pay attention. When it passes within the range of satellites, like Apophis will, that's historic. Distance is the filter that separates curiosities from nightmares. And then comes probability. This is where things get tricky. An asteroid either hits or it doesn't. There's no halfway. But when you discover one, your data is incomplete. You know its position on a few nights, maybe its brightness, maybe a radar ping. From that, you project an orbit. But with so little information, your orbit is fuzzy. Like sketching the outline of a shadow. Within that fuzziness lies uncertainty. The asteroid might hit, or it might miss. The math gives you a percentage. That percentage is not destiny. It's a placeholder. The more you observe, the smaller the fuzziness gets, the sharper the orbit becomes, the more the probability collapses towards zero, or, rarely, towards certainty. But in those early days, the probabilities can look terrifying. And that's exactly what happened with Apophis. At its peak, the chance of impact in 2029 was 2.7%. That doesn't sound like much. But imagine playing Russian roulette with a gun that had 37 chambers, and one of them loaded. Would you pull the trigger? That's why Apophis rattled the scientific community. Not because doom was guaranteed, but because it wasn't impossible. And in space, not impossible is enough to matter. To make sense of these probabilities, scientists use the Torino scale. Picture it as a color-coded thermometer of asteroid danger. 0 means no chance of impact. 1 means a routine discovery, no real risk. 2 to 4 means something worth tracking closely. 5 to 7 means a serious threat. 8 to 10. Catastrophe certain. The kind of event that rewrites history. Apophis hit a 4. The highest ever recorded. For months in 2004, it sat there, glaring from the charts, a reminder that our planet is not immune. That number alone was enough to spark urgent funding requests, emergency meetings, and sleepless nights. But here's where probability becomes even more sinister. Because even when the odds are low, the consequences are so high that you can't ignore them. A 1% chance of global disaster is not something you brush aside. Even a 0.01% chance, if the damage is measured in millions of lives, demands attention. That's why planetary defense is not about certainty, it's about vigilance. About respecting the math before the rock becomes unavoidable. Now consider the statistics of impact over time. Large impacts are rare, yes. A 300-meter asteroid like Apophis hits Earth on average once every 80,000 years. That sounds comforting, until you realize that averages lie. They don't mean, not in our lifetime. They mean that the universe rolls dice every year, and eventually, the bad roll comes up. It could be 100,000 years from now. It could be tomorrow. Chelyabinsk proved this. Nobody saw it coming. A 20-meter asteroid slipped through our defenses and exploded over Russia. Statistically, something that size hits Earth once every 50 years or so. But we didn't know about that one. We didn't track it. It just appeared, a sudden fireball in the morning sky, shattering glass and rattling nerves. If it had entered at a slightly different angle, over a populated megacity instead of a sparsely inhabited region, the casualties could have been catastrophic. This is the haunting reality. We know about the big ones, the kilometer-wide monsters. They're easier to spot. They're rare. We've mapped most of them. But the mid-sized killers, the 100 to 300 meter range, we've only found a fraction. Thousands remain hidden. Lurking. Waiting. And every year, more slip past. In 2019, a 100-meter asteroid designated 2019 OK zipped past Earth at less than 1/5 the distance to the Moon. Astronomers only spotted it a few days before the pass. Too late to act, if it had been on target. That one could have leveled an entire state. That's why Apophis matters so much. Not because it will hit, but because it forced us to confront the probabilities. To admit that the universe is not safe. That civilization lives on borrowed luck. And luck, as history shows, runs out. The dinosaurs learned that lesson 66 million years ago. Chicxulub, the 10-kilometer asteroid that ended their reign, struck with the force of 100 million megatons. It didn't matter that it was a 1 in 100 million years event. It happened. And when it did, it reset the planet. The age of reptiles ended. The age of mammals began. Today, we live in their shadow, survivors only because luck swung our way. But luck is not a strategy. That's why scientists talk about probabilities not to scare, but to prepare. Because the numbers tell a simple truth, impact is inevitable, given enough time. Our only choice is whether we meet it unprepared, like the dinosaurs, or prepared, like a species that finally learned to think ahead. And here's the strange paradox of probability. Certainty can be less frightening than maybe. If scientists announced tomorrow that a large asteroid would hit in 2129, humanity would mobilize. We'd build defenses. We'd fund missions. We'd prepare. But when the odds hover in the murky range of 1%, 0.5%, 0.1%, that's when politicians stall. That's when budgets get cut. That's when the danger hides in plain sight. And that's why Apophis is so important. It wasn't a certainty. It was a maybe. A maybe strong enough to jolt the system. A maybe that forced humanity to finally start planning for the inevitable. Because one day, the math will line up again. The size, the distance, the probability will combine, and the scale will shift from yellow to red. And when that happens, all the lessons from Apophis will be tested. But before we talk about deflection strategies and spacecraft missions, let's ground ourselves again in history. Because Apophis wasn't the first rock to make us nervous. And it won't be the last. Earth has been hit before. Many times. Each impact leaving scars written into our planet's crust. Scars that tell the story of what happens when probability collapses to certainty. And those scars reveal just how close we already live to chaos. If you want to know Earth's future, look at its scars. Our planet is covered in reminders that the cosmos does not forgive. Every crater, every blast site, every strange circular depression is a signature of the times when probability collapsed into certainty and space came calling. The most famous of these scars is Chicxulub. 66 million years ago, a 10-kilometer asteroid slammed into what is now the Yucatan Peninsula in Mexico. The energy released was equivalent to about 100 million megatons of TNT, more powerful than all the nuclear weapons ever built, multiplied 1,000,000 times. The crater it left behind spans 180 kilometers across, though much of it is buried under rock and ocean. But the real devastation wasn't local. The impact vaporized rock and sulfur, launching a cloud of dust into the sky that circled the globe. Day turned to night. Photosynthesis collapsed. Temperatures plummeted. Acid rain fell. 75% of species on Earth vanished, including the dinosaurs. It was the end of one era and the beginning of another. Without Chicxulub, mammals might never have risen. Without Chicxulub, humans might never have evolved. That's the lesson written in stone: impacts don't just kill. They reset the clock of evolution. They change the entire trajectory of life. Of course, Chicxulub was a once in hundreds of millions of years event. Apophis is nowhere near that scale. But smaller impacts have left their marks too, and their stories are just as important. Travel back to June 30, 1908, in the remote forests of Siberia. At 7:17 a.m., a fireball blazed across the morning sky. A moment later, it exploded with the force of a 15-megaton bomb. The shockwave flattened 2,000 square kilometers of forest, an area larger than Tokyo. Trees fell in radial patterns, like matchsticks knocked flat. Windows shattered hundreds of kilometers away. People were knocked off their feet in distant villages. The Tunguska event, as it came to be known, was caused by an asteroid or comet fragment about 50 to 80 meters across. It never even hit the ground. It exploded in the atmosphere in what's called an airburst, releasing its energy high above the surface. If that explosion had occurred over St. Petersburg or London, millions would have died instantly. Instead, by sheer luck, it happened over one of the most remote regions on Earth. Civilization got a warning shot. Fast forward to February 15, 2013. A clear winter morning in Chelyabinsk, Russia. People were commuting to work, children were in school, and then the sky lit up. A fireball brighter than the sun streaked overhead. Seconds later, a shockwave shattered windows across the city, injuring over 1,500 people. Car alarms blared. Walls cracked. Chaos erupted. That rock was only 20 meters wide. And yet, the energy it released was equivalent to nearly 500 kilotons of TNT, more than 30 times the Hiroshima bomb. If it had been larger, if it had entered at a slightly different angle, the outcome could have been catastrophic. These are not ancient events lost to deep time. They are modern. Tunguska in 1908. Chelyabinsk in 2013. Both within living memory. Both reminders that we are still in the crosshairs. And those are just the big ones. The truth is, Earth is hit by space debris constantly. Tiny grains of dust burn up as shooting stars every night. Larger objects, a few meters across, strike every few years, usually over the ocean. The atmosphere protects us most of the time, but not always. And as Chelyabinsk proved, even a small rock can cause mass injuries in a modern city. So when scientists talk about Apophis, they're not crying wolf. They're reading the scars. They know what even small impacts can do. They've seen forests leveled, cities rattled, species erased. And they understand that a 340-meter asteroid is in a completely different league. Think of it this way. Chelyabinsk was 20 meters. Tunguska was maybe 60. Apophis is more than 5 times larger than Tunguska. But the damage scales exponentially. The energy of an impact grows with the cube of its diameter. That means Apophis carries thousands of times more destructive potential than Chelyabinsk, and hundreds of times more than Tunguska. That's why astronomers shiver when they hear its name. Not because it will hit in 2029, it won't. But because they've seen the scars. They know what even smaller rocks have done. And they know Apophis is exactly the kind of object that, one day, could write a new chapter in Earth's history. And there's something else about scars. They remind us of our ignorance. The Chicxulub crater wasn't even confirmed until the 1990s. Tunguska wasn't seriously studied until decades after the blast. Chelyabinsk caught us completely by surprise. Over and over, humanity has been blindsided, only realizing the truth after the damage was done. Apophis, in that sense, is different. We see it coming. We know the date. We know the distance. We have time. And that makes 2029 unique. For the first time in history, we will witness an asteroid of that scale pass close enough to be studied in detail, without the consequence of impact. It's as though the cosmos is giving us a rehearsal. A warning wrapped in mercy. But mercy is not guaranteed. Not for the next one. Not for the ones still hidden. That's why planetary defense has become more than just an academic exercise. It's a race against probability. A race to find the next Apophis before it finds us. Because while Chicxulub, Tunguska, and Chelyabinsk are stories of the past, they are also previews of the future. And here's the strange irony. Every crater, every blast site, every scar tells a story of destruction. But together, they tell a story of survival too. Earth has been hit countless times, and yet life persists. We persist. The scars are warnings, yes, but they are also evidence that survival is possible. The question is whether we'll take the warnings seriously enough to prepare. Because the next chapter is unwritten. And as Apophis looms, it forces us to ask, will we learn from the scars of the past, or will we add another one to the tally? The answer lies not in the rocks themselves, but in us. But before we look at humanity's response, let's zoom out again. Because asteroids don't travel alone. They are fragments of larger families, shards of cosmic collisions, children of the asteroid belt. And to understand Apophis, we need to understand where it came from. Because every scar has a source. And every rock has a story. Every rock in space has a story. Some are fragments from the dawn of the solar system, leftovers from the swirling disk of dust and gas that formed the planets. Others are shards of ancient collisions, splintered off larger worlds and sent drifting into space. Apophis is one of these wanderers, and to understand it, we have to go back, 4.5 billion years back, to the beginning. In those first chaotic millions of years, our solar system was a violent place. The young sun was surrounded by a swirling protoplanetary disk. Dust grains collided, stuck together, grew into pebbles, then boulders, then planetesimals. These building blocks smashed and merged, some forming the planets we know today. Others never quite made it. Instead, they became the asteroids, frozen remnants of a creation that never finished. Most of them still live in the asteroid belt, that vast region between Mars and Jupiter. Picture it not as a solid wall of rocks but as a sparse scattering. The total mass of the entire belt is less than 1/20th of the Moon's. But what it lacks in density, it makes up for in chaos. Over billions of years, Jupiter's immense gravity has stirred the belt like a cosmic spoon, creating zones of stability and instability. The unstable zones, called Kirkwood gaps, are highways leading asteroids out of the belt and toward the inner solar system. That's likely where Apophis began. Long ago, it was part of a larger body orbiting quietly in the main belt. Then, through a chain of collisions and gravitational nudges, it was ejected onto a path that intersected with Earth's orbit. From then on, it became what we call an Apollo-class asteroid, named for the first of its kind discovered, a group of near-Earth objects whose orbits cross our planets. And once an asteroid becomes an Apollo, it's only a matter of time before close encounters begin. But here's the thing. These encounters aren't rare. They're inevitable. The solar system is not clockwork perfection. It's chaos hidden inside order. Every orbit is tugged by the gravity of planets, every spin is twisted by the subtle push of sunlight. Over centuries and millennia, these tiny nudges add up. Orbits shift. Paths cross. What looks stable becomes unstable. That's why no asteroid is truly safe forever. Apophis is proof of that. For decades, its orbit was just far enough from ours that no one paid attention. Then the math caught up, and suddenly it was a threat. Not because its nature changed, but because the geometry did. That's the unsettling truth, danger isn't always a matter of size. Sometimes, it's just a matter of timing. Think of it like traffic. Two cars can circle a roundabout for hours without colliding. But if one of them arrives at just the wrong moment, the geometry shifts. Suddenly, they're on a collision course. Asteroids are the same. Billions orbit the Sun without issue. But when timing aligns, when the orbits cross just right, or just wrong, impact becomes inevitable. And the solar system doesn't just produce random rocks. It produces families. Astronomers have identified clusters of asteroids with similar orbits, tracing them back to ancient collisions. Some families are hundreds of millions of years old, their members still spreading out from a single catastrophic breakup. These families act like cosmic seedbeds, constantly sending fragments into unstable regions where Jupiter or Mars can sling them toward Earth. Apophis may belong to one such family. Its stony composition and reflective properties suggest it was born from a shattered parent body in the inner belt. Over millions of years, it drifted, nudged by resonances with Jupiter, until it slipped into an Earth-crossing orbit. By the time Tucker, Thalin, and Bernardi spotted it in 2004, it had been circling near us for centuries. We just hadn't noticed. This is what makes the threat of asteroids so unsettling. They aren't invaders. They're neighbors. They've been here all along, circling quietly, waiting for the geometry to betray us. Apophis didn't arrive suddenly. It didn't fall out of the sky like a bolt from nowhere. It was always there. The only thing that changed was our awareness. And our awareness is still incomplete. Astronomers estimate there are hundreds of thousands of near-Earth objects larger than 100 meters. We found perhaps a third. The rest are invisible to us, lurking in the dark, waiting for discovery. Some are hidden in the glare of the sun, where telescopes can't see. Others approach from angles that make them hard to detect. That means at any moment, there could be another Apophis out there, circling unnoticed. This is why the study of asteroid origins matters. It's not just about curiosity. It's about prediction. If we know which families tend to send fragments our way, we know where to look. If we understand the chaos of orbital dynamics, we can better model which asteroids are likely to drift into Earth's path. Every bit of knowledge sharpens our warning time, and warning time is survival. Because here's the sobering truth, the difference between a harmless pass and a global disaster is often just a few thousand kilometers. A nudge here, a tug there, and an asteroid that would have missed instead collides. When you're talking about objects moving at tens of kilometers per second, tiny changes add up fast. Apophis embodies that razor's edge. In 2029, it will miss by 31,000 kilometers. That sounds comfortable, but in astronomical terms, it's nothing. If it had been on a slightly different path, if its orbit had shifted just a fraction, it could have struck. And the chaos of the solar system guarantees that eventually, one of its cousins will. That's why scientists talk about when, not if. The scars on Earth prove it. The asteroid belt guarantees it. And the families of rubble drifting through space are still sending children our way. Apophis is simply the one we spotted. And that brings us to the most haunting part of its story. Because while we talk about Apophis as an opportunity, as a harmless spectacle in 2029, we can't ignore the fact that we got lucky. Lucky that it will miss. Lucky that it won't pass through a gravitational keyhole that sets up a future strike. Lucky that it was discovered early enough to be tracked, instead of appearing in the sky one morning like Chelyabinsk. Luck is not a defense strategy. Chaos does not negotiate. The asteroid belt will keep sending us reminders, whether we're ready or not. And Apophis, the chaos god, is not finished teaching us. Because when it threads the needle in 2029, we'll get to watch chaos in action. Earth's gravity will tug at it, reshaping its path, maybe even reshaping its body. The asteroid belt sent it our way long ago. Now we get to see what happens when chaos collides with proximity. But before we watch that moment unfold, let's ask a deeper question. What exactly happens if one of these rocks doesn't miss? What are the mechanics of destruction? We know the scars. We've seen the aftermath. But what would it look like, step by step, if a 300-meter asteroid really did strike Earth? That's where our journey takes us next. Let's imagine, just for a moment, that the math had come out differently. That the probabilities hadn't collapsed to zero. That instead of missing in 2029, Apophis had been on a direct course for Earth. What would happen? What would it look like? And what would it mean for civilization? First, the approach. For weeks before impact, Apophis would be visible to telescopes, tracked with increasing precision. By the final days, its orbit would be locked in. There would be no doubt. Humanity would know the date, the hour, perhaps even the minute of collision. The world would watch it grow brighter in the sky, a moving star that no one could ignore. The media frenzy would be unlike anything in history. 12 hours before impact, Apophis would shine like a faint star to the naked eye. 6 hours before, it would be unmistakable, a glowing point crossing the heavens. As it entered Earth's atmosphere, traveling at nearly 30 kilometers per second, it would transform into a fireball brighter than the sun. The air in front of it would compress, heating to tens of thousands of degrees, igniting the sky. Then, the strike. If Apophis hit land, the devastation would be apocalyptic on a regional scale. The energy released would be equivalent to about 1,000 megatons of TNT. That's 20 times more powerful than the largest nuclear weapon ever detonated. The crater would span several kilometers across, perhaps as wide as downtown Los Angeles. Everything within tens of kilometers would be vaporized instantly. Shockwaves would flatten buildings and forests 100 kilometers away. Firestorms would rage across entire regions, sparked by thermal radiation igniting everything flammable. If it struck near a city, millions would die in seconds. The destruction wouldn't stop at the impact site. Dust and debris hurled into the atmosphere could darken the skies for months. Crops could fail across continents. Global temperatures could drop. It wouldn't be extinction, but it could be famine, war, and economic collapse on a scale unseen in modern times. If Apophis hit the ocean, the scenario would be different but no less terrifying. The asteroid's mass plunging into water at cosmic speed would displace billions of tons instantly. Tsunamis hundreds of meters high would race outward. Coastal cities across oceans could be wiped out within hours. Imagine New York, Miami, Tokyo, and Shanghai all drowning on the same day. The death toll could reach into the hundreds of millions. And remember, this is just a 340-meter asteroid. Not a dinosaur killer. Not a world ender. Just a rock big enough to wipe out nations. That's the unsettling truth. Civilization doesn't need an extinction-level event to collapse. It only needs a regional catastrophe in the wrong place. We can run the physics. A rock 340 meters across, with a density of about 3,000 kilograms per cubic meter, masses roughly 100 billion kilograms. Multiply that by its velocity, say, 30,000 meters per second, and the kinetic energy is staggering, around 5 times 10 to the power of 18 joules. To put that in perspective, that's about 1,200 times the yield of the world's entire nuclear arsenal combined. All unleashed in a single instant, on a single unlucky spot. And here's the detail that most people miss. The atmosphere doesn't protect us from something this big. For small objects, yes, the friction rips them apart, burns them to dust. Chelyabinsk exploded at altitude because it was only 20 meters wide. Tunguska disintegrated because it was maybe 60 meters. But Apophis is too massive. It would punch through the atmosphere like tissue paper. The fireball would be visible across continents, the shockwave audible for thousands of kilometers. The aftermath wouldn't just be physical. It would be psychological. Civilization thrives on certainty, on stability. An impact like Apophis would shatter that illusion. Suddenly, every human would understand that Earth is not safe, that the cosmos does not care, that everything we've built stands at the mercy of chance. Religions would react. Governments would reel. Markets would collapse. The world would never be the same. And yet, even in that nightmare, there would be survivors. Life would go on. Humanity is resilient. But the scars, physical, cultural, psychological, would last for generations. Children born after the strike would grow up in a world shaped by it, just as our world was shaped by Chicxulub, Tunguska, and Chelyabinsk. That's why planetary defense experts insist that Apophis is not just a curiosity. It's a warning. It's the scale model of catastrophe. If a rock this size were on a collision course, our options would be limited. Kinetic impactors, like the DART mission tested in 2022, could work if launched years in advance. A gravity tractor, parking a spacecraft nearby to tug the asteroid with subtle force, might help if we had decades. Nuclear options remain the last resort, risky but possible. But if we discovered Apophis only months before impact, there would be no defense. Just evacuation, impossible on a global scale, or prayer. And that is the razor edge we live on. Because Apophis is only one of thousands. We spotted it early, by luck. Others, like 2019 OK, slipped past detection until days before they skimmed Earth. That's the nightmare scenario, a 300-meter asteroid, unknown until it appears in the sky, too late to act. Civilization undone, not by malice, not by war, but by negligence. This is why the 2029 flyby matters. It isn't just a spectacle. It's a dress rehearsal. A chance to measure, to learn, to prepare. Because the day may come when the scenario we just imagined isn't hypothetical. When the fireball isn't a thought experiment but a headline. When the chaos god doesn't miss. And here's the uncomfortable truth, if that day comes, it won't feel like an alien invasion. It won't feel like a Hollywood blockbuster. It will feel like physics. Cold, unstoppable, indifferent. A rock on a path. A date on a calendar. And then, impact. But 2029 is not that day. Instead, it is the opposite. A moment of safety. A close call that ends in survival. And that survival gives us a gift, the chance to watch, to measure, to prepare for the day when safety runs out. Because chaos doesn't give second chances often. And when it does, only fools ignore them. Which leads to the next question. What exactly are we doing to prepare? How do you defend a planet from a rock the size of a mountain? The answers are both reassuring and terrifying. And they begin with a mission that slammed into an asteroid just to see what would happen. For centuries, the idea of defending Earth from an asteroid belonged to science fiction. Writers imagined rockets armed with nuclear warheads, desperate missions to blow up rocks at the last second, brave crews flying into certain death. It was thrilling. It was dramatic. But it wasn't real. Not until 2022. That year, humanity threw its first punch at the cosmos. The mission was called DART, the Double Asteroid Redirection Test. A small spacecraft, no larger than a vending machine, with one goal, slam into an asteroid and see if it moved. No nuclear weapons, no drama, just pure physics. The target was a binary system called Didymos and Dimorphos. Didymos is the larger asteroid, about 780 meters wide. Dimorphos is its smaller moon, about 160 meters across. They orbit each other like a cosmic dance, circling the sun together. NASA chose Dimorphos because it was small enough to be nudged, but large enough to measure the results. On September 26, 2022, after a 10-month journey across 11 million kilometers of space, DART approached at 22,500 kilometers per hour. Cameras on board streamed live images to Earth as the asteroid grew larger and larger. First a speck, then a potato-shaped rock, then boulders and ridges. And then, the feed cut to static. Impact. The world held its breath. Scientists scrambled to telescopes across the planet. Space probes turned their instruments toward the system. And slowly, the data came in. Dimorphos had been nudged. Not by much. But enough. Its orbital period around Didymos had shortened by 32 minutes. That might sound trivial, but in cosmic terms, it was historic. For the first time, humanity had changed the path of a celestial body. The implications were staggering. DART proved that planetary defense is not just a dream. It's a science. If you find an asteroid early enough, if you have years or decades of warning, you can move it. Not with nukes. Not with magic. With momentum. A kinetic impactor, a spacecraft slamming into rock at high speed, can make the difference between a hit and a miss. And the effect was larger than expected. Scientists predicted a shift of maybe 10 minutes. They got 3 times that. Why? Because Dimorphos wasn't a solid boulder. It was a rubble pile. The impact blasted material into space, like a shotgun blast of debris. That ejected mass acted like a rocket plume, amplifying the push. What should have been a gentle tap became a solid shove. This matters deeply for Apophis. Remember, we still don't know whether it's a solid chunk or a rubble pile. The DART experiment showed that rubble piles are more responsive to impacts than expected. That means if we ever had to deflect Apophis, and if it turns out to be rubble, we might have a better chance than feared. But there's another lesson too. Timing is everything. DART worked because we tested it on a harmless target. But if an asteroid like Apophis were discovered only months before impact, no spacecraft could reach it in time. Planetary defense requires years of warning. Decades, ideally. Without warning, there is no defense. That's why detection is just as important as deflection. You can't move what you don't see. And right now, our eyes on the sky are still limited. Ground-based telescopes can't scan the regions near the sun's glare. That's why NASA is building the NEO Surveyor, a space telescope designed to hunt for asteroids from orbit, scheduled for launch later this decade. With infrared eyes, it will spot the dark, heat-radiating rocks that are invisible to visible light telescopes. Because let's be clear. Apophis was a wake-up call. DART was a proof of concept. But we are still unprepared. If the Chaos God, or one of its cousins, were actually on a collision course today, our survival would depend almost entirely on luck. And luck, as history shows, cannot be trusted. Still, DART gave us something priceless. It gave us proof. Proof that humanity can reach out across millions of kilometers and change destiny with a machine no bigger than a refrigerator. Proof that we don't have to wait helplessly for impact. Proof that we can fight back. It also gave us practice in something less glamorous but just as critical: coordination. DART wasn't just NASA. It was international. Telescopes in Chile, South Africa, and the Canary Islands contributed. The European Space Agency is following up with a mission called Hera, set to arrive at Didymos in 2026 to study the aftermath in detail. Together, they mark the beginning of a new field: planetary defense as a global science, not just a local experiment. And here's where Apophis ties back in. In 2029, when it schemes past Earth, it will be close enough for radar to map every meter of its surface. Close enough for spacecraft like OSIRIS-APEX to rendezvous and watch in real time. Close enough that ordinary people will see it with their own eyes. That flyby will be the ultimate test, not a test of deflection, but of observation. We'll learn whether Apophis is a rubble pile or a monolith, whether its spin changes, whether Earth's gravity shifts its orbit. That knowledge, combined with DART's proof of concept, will arm us with the tools to face the next threat. Because the next threat is coming. Statistically, it's inevitable. The scars on Earth prove it. Chicxulub. Tunguska. Chelyabinsk. The probabilities guarantee that another rock, somewhere, sometime, will line up with our orbit. The only question is whether we'll see it coming, and whether we'll be ready to act. DART was humanity's first punch. Apophis will be our first close-up lesson. Together, they form the foundation of a new era, the age of planetary defense. But the story doesn't end there. Because if Apophis taught us to measure, and DART taught us to push, there remains a deeper, more unsettling question. What if, one day, we push too late? What if detection fails, warning comes short, and the rock is already on its way? That's when humanity faces the last resort. The one option we've always feared, but may one day be forced to use. And that option is nuclear. For centuries, the idea of defending Earth from an asteroid belonged to science fiction. Writers imagined rockets armed with nuclear warheads, desperate missions to blow up rocks at the last second, brave crews flying into certain death. It was thrilling. It was dramatic. But it wasn't real. Not until 2022. That year, humanity threw its first punch at the cosmos. The mission was called DART, the Double Asteroid Redirection Test. A small spacecraft, no larger than a vending machine, with one goal: slam into an asteroid and see if it moved. No nuclear weapons, no drama, just pure physics. The target was a binary system called Didymos and Dimorphos. Didymos is the larger asteroid, about 780 meters wide. Dimorphos is its smaller moon, about 160 meters across. They orbit each other like a cosmic dance, circling the sun together. NASA chose Dimorphos because it was small enough to be nudged, but large enough to measure the results. On September 26, 2022, after a 10-month journey across 11 million kilometers of space, DART approached at 22,500 kilometers per hour. Cameras on board streamed live images to Earth as the asteroid grew larger and larger. First a speck, then a potato-shaped rock, then boulders and ridges. And then, the feed cut to static. Impact. The world held its breath. Scientists scrambled to telescopes across the planet. Space probes turned their instruments toward the system. And slowly, the data came in. Dimorphos had been nudged. Not by much. But enough. Its orbital period around Didymos had shortened by 32 minutes. That might sound trivial, but in cosmic terms, it was historic. For the first time, humanity had changed the path of a celestial body. The implications were staggering. DART proved that planetary defense is not just a dream. It's a science. If you find an asteroid early enough, if you have years or decades of warning, you can move it. Not with nukes. Not with magic. With momentum. A kinetic impactor, a spacecraft slamming into rock at high speed, can make the difference between a hit and a miss. And the effect was larger than expected. Scientists predicted a shift of maybe 10 minutes. They got 3 times that. Why? Because Dimorphos wasn't a solid boulder. It was a rubble pile. The impact blasted material into space, like a shotgun blast of debris. That ejected mass acted like a rocket plume, amplifying the push. What should have been a gentle tap became a solid shove. This matters deeply for Apophis. Remember, we still don't know whether it's a solid chunk or a rubble pile. The DART experiment showed that rubble piles are more responsive to impacts than expected. That means if we ever had to deflect Apophis, and if it turns out to be rubble, we might have a better chance than feared. But there's another lesson too. Timing is everything. DART worked because we tested it on a harmless target. But if an asteroid like Apophis were discovered only months before impact, no spacecraft could reach it in time. Planetary defense requires years of warning. Decades, ideally. Without warning, there is no defense. That's why detection is just as important as deflection. You can't move what you don't see. And right now, our eyes on the sky are still limited. Ground-based telescopes can't scan the regions near the sun's glare. That's why NASA is building the NEO Surveyor, a space telescope designed to hunt for asteroids from orbit, scheduled for launch later this decade. With infrared eyes, it will spot the dark, heat-radiating rocks that are invisible to visible light telescopes. Because let's be clear. Apophis was a wake-up call. DART was a proof of concept. But we are still unprepared. If the Chaos God, or one of its cousins, were actually on a collision course today, our survival would depend almost entirely on luck. And luck, as history shows, cannot be trusted. Still, DART gave us something priceless. It gave us proof. Proof that humanity can reach out across millions of kilometers and change destiny with a machine no bigger than a refrigerator. Proof that we don't have to wait helplessly for impact. Proof that we can fight back. It also gave us practice in something less glamorous but just as critical, coordination. DART wasn't just NASA. It was international. Telescopes in Chile, South Africa, and the Canary Islands contributed. The European Space Agency is following up with a mission called Hera, set to arrive at Didymos in 2026 to study the aftermath in detail. Together, they mark the beginning of a new field, planetary defense as a global science, not just a local experiment. And here's where Apophis ties back in. In 2029, when it schemes past Earth, it will be close enough for radar to map every meter of its surface. Close enough for spacecraft like OSIRIS-APEX to rendezvous and watch in real time. Close enough that ordinary people will see it with their own eyes. That flyby will be the ultimate test, not a test of deflection, but of observation. We'll learn whether Apophis is a rubble pile or a monolith, whether its spin changes, whether Earth's gravity shifts its orbit. That knowledge, combined with DART's proof of concept, will arm us with the tools to face the next threat. Because the next threat is coming. Statistically, it's inevitable. The scars on Earth prove it. Chicxulub. Tunguska. Chelyabinsk. The probabilities guarantee that another rock, somewhere, sometime, will line up with our orbit. The only question is whether we'll see it coming, and whether we'll be ready to act. DART was humanity's first punch. Apophis will be our first close-up lesson. Together, They form the foundation of a new era, the age of planetary defense. But the story doesn't end there. Because if Apophis taught us to measure, and Dart taught us to push, there remains a deeper, more unsettling question. What if, one day, we push too late? What if detection fails, warning comes short, and the rock is already on its way? That's when humanity faces the last resort. The one option we've always feared, but may one day be forced to use. And that option is nuclear. When people hear the phrase, planetary defense, their minds often leap to one image: nukes in space. It's the Hollywood solution, dramatized in films from Armageddon to Deep Impact, astronauts riding rockets, nuclear warheads detonating at the last second, Earth saved in a blinding flash. It's cinematic. It's thrilling. And it's also, in a strange way, not entirely wrong. Because nuclear weapons are the last resort. They are the option no one wants to use, but everyone knows might one day be necessary. Why? Because nukes deliver the one thing asteroids respect: energy. A nuclear warhead detonated in space releases millions of times more energy than a conventional bomb. Against a large, fast-moving rock, that energy could make the difference between impact and survival. But the way you use it matters. There are three main strategies. The first is direct detonation on the surface. Imagine slapping a warhead against the asteroid's skin and lighting it off. The explosion vaporizes part of the surface, blasting debris outward like a rocket engine. That recoil can nudge the asteroid onto a new path. The second is subsurface detonation. In theory, if you drilled into the asteroid, or landed a penetrator, you could bury the warhead before detonation. That would channel more of the energy inward, fracturing the rock more dramatically. But this approach is riddled with risks. Drill too shallow, and you waste energy. Drill too deep, and you could shatter the asteroid into fragments, some still headed for Earth. One rock becomes many bullets. The third, and most widely discussed among scientists, is standoff detonation. In this method, the bomb doesn't touch the asteroid. Instead, it detonates at a distance, bathing the rock in a flood of X-rays and gamma radiation. That radiation vaporizes part of the surface facing the blast, again producing a recoil. The advantage is control. You don't risk breaking the asteroid into dangerous pieces. You push instead of pulverize. Which of these would work best against Apophis? That depends entirely on what Apophis is made of. If it's a rubble pile, held together loosely by gravity, detonating on or beneath the surface could scatter it into a deadly swarm. In that case, a standoff detonation would be safer. If it's more solid, direct contact might deliver a stronger shove. But here's the point: without knowing its internal structure, you're gambling with survival. And that's the haunting part. Nuclear weapons are powerful, but they're also blunt. They require precision in a situation where precision is hard to come by. You need exact knowledge of the asteroid's mass, density, spin, and composition. A miscalculation could mean failure. Then there are the political risks. Nuclear weapons in space violate international treaties, including the 1967 Outer Space Treaty. The very idea of launching nuclear warheads into orbit raises fears of weaponization, of accidental detonation, of mistrust between nations. Who controls the warhead? Who decides when to launch? If a misfire occurs, who takes responsibility? The moral weight is enormous. But scientists don't dismiss the nuclear option lightly. They understand the stakes. If Apophis, or a larger cousin, were on a collision course with only months of warning, kinetic impactors like Dart wouldn't cut it. A gravity tractor would be useless. The only hope would be the raw, brute force of nuclear energy. And in that moment, humanity would face a choice: break treaties, risk controversy, or face annihilation. Some models are reassuring. Studies show that a 1 megaton warhead, detonated at the right distance, could nudge a 300-meter asteroid like Apophis just enough to miss Earth. Others suggest that a series of smaller detonations could be even more effective, spreading the push over time. But every scenario depends on early detection. The more time you have, the smaller the nudge required. Wait too long, and even 1,000 megatons won't matter. This is why planetary defense experts repeat the mantra, find them early. Nukes are not a plan. They are a parachute. And parachutes are useless if you don't know you're falling. Still, there's something sobering about admitting we might one day need them. For all our talk of peace, for all our treaties, for all our fear of nuclear weapons on Earth, their most important use may not be against each other, but against the sky. The weapons we built to destroy ourselves may one day save us. That irony is hard to ignore. But the nuclear option also carries a psychological cost. Imagine the announcement. Governments around the world confirm that an asteroid is on a collision course. They reveal the plan, to launch nuclear weapons into space. Some people cheer, others panic. Conspiracy theories explode. Markets crash. The very word, nuclear, ignites old Cold War fears. Even if the mission succeeds, the scars of fear and mistrust may linger for generations. And yet, the alternative is worse. Without action, the rock hits. The fireball blooms. Cities vanish. History resets. In that context, the nuclear option doesn't feel like a choice at all. It feels like inevitability. But let's step back. In 2029, we won't need nukes. Apophis will miss. Instead, it gives us the chance to practice, to prepare, to avoid ever reaching that last resort. DART showed that kinetic impactors can work. OSIRIS-APEX will study Apophis up close. NEO Surveyor will hunt for hidden rocks. Each step reduces the chance that we'll ever have to detonate warheads in space. Still, the fact remains, the nuclear option sits at the bottom of the toolbox, waiting. Humanity hopes never to open it. But we're comforted, strangely, that it's there. Because the cosmos doesn't negotiate. Asteroids don't care about treaties. And when the chaos god finally aims true, all that will matter is whether we're willing to use every tool we have. But there's another angle to planetary defense, one less destructive, one more elegant. Instead of smashing rocks or blasting them with nukes, what if we could simply tug them? Gently, invisibly, with the power of gravity itself? That's the idea behind the gravity tractor, a concept as subtle as it is brilliant. And that's where our story turns next. Asteroids are simple. They don't think, they don't plan, they don't care. They move according to physics, pulled by gravity, nudged by sunlight, shaped by collisions. They are chaos without malice. Humans, on the other hand, are complicated. We panic. We deny. We argue. We politicize. And when faced with a threat from the sky, our greatest obstacle may not be the rock itself but our own reactions to it. Consider the psychology of Apophis back in 2004. When word first spread that there was a 2.7% chance of impact in 2029, some scientists went sleepless. Some newspapers shouted doomsday headlines. But much of the public shrugged. 2.5 decades in the future. That was too abstract to feel real. The date sounded like science fiction. And when the probabilities fell to zero a few months later, interest collapsed entirely. The danger was forgotten. This is the first pattern, denial through distance. Humans are bad at imagining threats that unfold over decades. Climate change shows this. Pandemics showed it. Unless the danger is immediate, visible, and personal, we tend to push it aside. Asteroids fit neatly into that blind spot. But denial isn't the only response. The opposite, panic, is just as dangerous. Imagine the announcement, Apophis will strike Earth in 2036. Even if the impact zone were uncertain, even if governments had decades to act, the immediate human reaction would be chaos. Markets would crash. Cities near possible impact zones might empty. Misinformation would explode. Conspiracy theories would flourish, claims that the impact was invented, or that elites had secret bunkers, or that aliens were involved. Trust in institutions would erode. This is the paradox of planetary defense: tell people too little, and they won't prepare. Tell them too much, and they may collapse under fear. The balance is fragile. Transparency must walk hand in hand with reassurance. Governments know this. That's why, historically, officials have been cautious about announcing asteroid risks. When Apophis was discovered, NASA was careful to explain the numbers, to contextualize the probabilities. But even so, the word collision escaped, and headlines spun it into apocalypse. Some critics accused scientists of fearmongering. Others accused them of cover-ups. The truth was somewhere in between. Scientists were simply doing their job, updating probabilities as new data came in. But once the public narrative took hold, control was lost. This points to a deeper issue: trust. Planetary defense depends not just on rockets and telescopes but on whether people believe the institutions giving them information. If trust is high, warnings are heeded, cooperation follows. If trust is low, chaos spreads faster than the asteroid. International politics complicates things further. What if Apophis were predicted to hit within the borders of one nation, but action required global cooperation? Would rival nations set aside differences to save millions of strangers? Or would politics paralyze the response? History offers mixed evidence. During disasters like tsunamis and earthquakes, nations often cooperate. But when survival is at stake, competition can flare. Who controls the spacecraft? Who funds the mission? Who decides whether to launch nuclear weapons into space? These are not trivial questions. They cut to the heart of sovereignty and power. And yet, there is hope. The DART mission showed what cooperation can look like. NASA led, but telescopes worldwide contributed. The European Space Agency is sending Hera to follow up. Planetary defense is one of the few challenges where humanity's interests align perfectly. An asteroid doesn't care about borders. It doesn't care about ideology. It threatens everyone equally. In that shared vulnerability lies the seed of unity. Apophis in 2029 could be the turning point. Millions of people will see it with their own eyes. For the first time, the danger won't be abstract. It will be visible, undeniable, crossing the night sky like a glowing reminder of our fragility. That spectacle could terrify, or it could inspire. It could spark fear, or it could spark a global movement to fund surveys, build defenses, and take the threat seriously. The outcome depends on how we frame it. If the narrative is doom, people will despair. If the narrative is opportunity, people may unite. Scientists, educators, storytellers, all play a role in shaping that frame. Do we tell the story of chaos, or the story of foresight? Do we emphasize helplessness, or resilience? There's also a cultural layer. Different societies interpret cosmic events differently. Some may see an asteroid as an omen, a sign from the heavens. Others may see it as a challenge to overcome. In mythology, Apophis was the serpent of chaos, fought by the sun god Ra every night. In 2029, that myth will play out in the sky, chaos approaching, humanity watching. How cultures respond may shape how governments act. And beyond governments, there's the individual response. What would you do if told a rock the size of a mountain was coming for Earth in your lifetime? Would you prepare? Would you deny? Would you panic? Or would you, strangely, find peace in the reminder that life is fragile? For some, cosmic threats inspire fear. For others, they inspire awe. Both reactions are human. Both matter. Here's the sobering truth: humanity's survival doesn't depend only on rockets. It depends on psychology. On politics. On trust. On whether we can act together before chaos arrives. Apophis may never strike. But it tests us nonetheless. It asks, Can we look decades ahead and choose foresight over fear? Can we cooperate across borders for survival? Can we hold steady when the cosmos throws dice at our planet? The answers aren't certain. But 2029 will bring us closer to finding out. Because when millions of eyes look up and see the chaos god streaking across the sky, shimmering closer than satellites, the question won't be whether Apophis will hit. The question will be whether we are ready for the one that does. And that readiness depends on more than science. It depends on us. Which leads to the next part of this story, the survey systems, the watchmen of the sky, the quiet sentinels scanning every night for the next Apophis. Because foresight begins with vision, and vision begins with seeing. Asteroids are not the problem. The real problem is ignorance. You can't defend against what you don't see. And for most of history, humanity lived blind. Every fireball was a surprise, every crater a shock. Even as recently as 2013, Chelyabinsk arrived without warning. A rock the size of a house slipped through our defenses, exploded over a Russian city, and reminded us how vulnerable we remain. That's why planetary defense begins not with rockets, but with telescopes. The watchmen of the sky. Quiet instruments scanning the heavens every night, catching faint dots of light sliding against the background stars. Each dot is measured, tracked, plotted. Each becomes a line of numbers, an orbit, a prediction, a risk assessment. The math begins only after the sighting. The first step is always seeing. The modern effort to catalog near-Earth objects started in earnest in the late 1990s. NASA was tasked with finding 90% of asteroids larger than 1 kilometer, objects large enough to cause global catastrophe. By 2010, that goal was nearly complete. We know where most of the giants are, and none of them threaten Earth in the next century. That was reassuring, but also misleading. Because smaller asteroids, in the 100 to 500 meter range, remain far less catalogued. And those are the city killers. The region devastators. The Apophis of the sky. Ground-based telescopes carry most of the burden. The Linear Survey in New Mexico, the Catalina Sky Survey in Arizona, Pan-STARRS in Hawaii, all have discovered thousands of asteroids. They work by taking repeated images of the same patch of sky, hours apart. Stars remain fixed. Asteroids move. A computer compares the frames, finds the wandering dots, and flags them for further study. Simple in principle, but powerful in practice. Still, ground surveys have blind spots. They can't see asteroids approaching from the direction of the sun. They can't always penetrate the faint darkness where small, dark objects hide. Weather and daylight limit their reach. That's where space-based surveys come in. NASA is preparing the NEO Surveyor, a dedicated space telescope set to launch later this decade. Unlike ground-based instruments, it will scan the sky in infrared, the spectrum of heat. Asteroids, even the darkest ones, glow faintly in infrared. By detecting that glow, NEO Surveyor will reveal rocks invisible to ordinary telescopes. From its position far from Earth's atmosphere, it will watch continuously, free of weather, free of day and night. Its mission: find 2/3 of potentially hazardous asteroids 140 meters or larger within a decade. Think about that. 2/3. That means even in the 2030s, a third will remain unknown. Thousands of rocks, some big enough to erase cities, will still lurk unseen. That's the sobering truth: no matter how many telescopes we build, the sky is vast. The hunt is never finished. But every new discovery is a victory. Every orbit plotted reduces uncertainty. Every potential Apophis identified decades in advance gives us the chance to act. And here's where the story turns strange. Because detection isn't just about safety, it's about psychology. The more rocks we find, the scarier the sky looks. Headlines about asteroid near misses multiply. Social media erupts with panic. People ask, are we in more danger than before? The answer is paradoxical. We're not. We're actually safer. We just know more. Awareness looks like danger, but in truth, ignorance was the real threat. This is why communication matters. Astronomers have to balance honesty with reassurance. When they say, an asteroid will pass within 2 million kilometers, the public hears, near miss. But in space terms, that's not close at all. The moon is 20 times nearer. And yet, without context, fear grows. The watchmen of the sky don't just scan, they also explain. They teach. They put dots of light into perspective. Still, the fear isn't misplaced. Because every so often, the dots line up wrong. That's what happened with Apophis in 2004. That's what could happen again with another asteroid tomorrow. And the only way to know is to keep watching. Here's the other challenge: money. Telescopes cost millions. Space missions cost billions. And budgets are finite. Politicians often ask, why spend so much on rocks that might never hit? The answer is simple: insurance. Planetary defense is the ultimate insurance policy. We pay billions now to avoid trillions in losses, and millions of lives, later. But insurance is never glamorous. Until the fire starts, people grumble about the premiums. Apophis may change that. When it sweeps past Earth in 2029, visible to the naked eye, billions of people will ask, what else is out there? That moment may be the biggest public relations campaign planetary defense will ever get. If governments are wise, they'll seize it. They'll point to the chaos god streaking across the sky and say, this is why we fund the watchmen. This is why we need more eyes on the dark. Because the alternative is blindness. And blindness, in the cosmos, is fatal. Detection isn't perfect. Some rocks will still surprise us. But the more we see, the more time we buy. And time is the currency of survival. A century of warning turns an impossible problem into a manageable one. A decade of warning gives us options. A year of warning gives us panic. A month gives us prayer. That's the scale. That's the difference between foresight and extinction. And so, night after night, telescopes sweep the heavens. Computers hum, processing frames. Astronomers log coordinates, calculate orbits, refine probabilities. It's quiet work, unglamorous work, often unnoticed. But it is, in many ways, the most important work humanity has ever done. Because without it, we are walking blind across a cosmic shooting range. The watchmen of the sky aren't just scanning for rocks. They're scanning for the future. For the day when another Apophis, or worse, appears. For the moment when probability collapses into certainty, and survival depends on whether we've seen far enough ahead. And here's the twist: Apophis itself, once feared, is now part of that safety net. By studying its orbit in exquisite detail, by tracking its every wobble, scientists refine the tools that will protect us from others. Apophis, the chaos god, has become a sentinel. But seeing is only the beginning. Knowing a threat exists is one thing. Deciding what to do about it is another. And that's where humanity's greatest test lies, not in telescopes, not in physics, but in the choices we make once the data is in. Because what good are watchmen if the city sleeps through the alarm? That's the question Apophis leaves us with. And to answer it, we need to explore what comes after detection, decision-making, coordination, and the will to act. Let's imagine the nightmare scenario. Astronomers confirm that a 300-meter asteroid is on a collision course with Earth, impact certain within 20 years. The math is clear, the orbit unshakable, the timeline unavoidable. Telescopes agree. Computers agree. There is no doubt. Now what? In the world of planetary defense, discovery is only the beginning. The harder part is deciding what to do. Who makes the call to act? Who pays for it? Who takes responsibility if something goes wrong? These questions are as heavy as the asteroid itself. At first, the scientists would announce their findings through the Minor Planet Center, the clearinghouse for asteroid discoveries. The information would be shared openly with the global community of astronomers. Within hours, amateur stargazers could confirm the object's position. In today's connected world, secrecy is almost impossible. The news would spread fast. From there, the data would reach national space agencies, NASA, ESA, JAXA, Roscosmos, CNSA. Each would run its own calculations, and within days, they would all agree, impact was coming. At that point, the problem would leap from the realm of science into the realm of politics. The United Nations has a standing committee for exactly this, the International Asteroid Warning Network, IAWN. Its job is to coordinate communication between governments, ensuring everyone sees the same numbers. Alongside it sits the Space Mission Planning Advisory Group, SMPAG, created to discuss possible responses. On paper, the framework exists. But paper is one thing, action another. Because the next step requires commitment. Someone must fund a mission. Someone must build spacecraft, test engines, plan trajectories. And space missions take years. Even the fastest planetary defense effort would require half a decade from concept to launch. Delay could mean doom. Here's the dilemma: space is global, but politics is local. Suppose the asteroid's impact zone is projected over Asia. Will Europe pay for the mission? Suppose it threatens Africa. Will the United States build the deflection spacecraft? Every nation has its own priorities, its own budget constraints, its own public opinion to manage. Convincing them to act together quickly is harder than moving the asteroid itself. Then there's the question of authority. Who has the right to launch a nuclear device into space, if that becomes necessary? The United Nations? The United States? A coalition? And what if the mission fails and fragments of the asteroid still strike Earth? Who bears responsibility for the casualties? History suggests cooperation is possible but messy. During natural disasters, nations often rush aid across borders. But during crises involving survival, competition can flare. Imagine the power struggle. The nation that controls planetary defense technology controls not just survival but prestige. Would rivals trust each other enough to share that control? Or would mistrust paralyze action until it's too late? This is why Apophis matters, even though it won't hit. It gives humanity a rehearsal, not just scientifically but politically. It forces governments to practice coordination, to test communication channels, to debate protocols before the sky is truly falling. In 2029, when Apophis streaks across the heavens, the world's leaders will have to answer questions from their people. They'll have to explain what planetary defense is, why it matters, and who makes the decisions. That public conversation could shape how the real crisis plays out. And here's the unsettling truth: decision-making might be the weakest link. Technologically, we know how to move small asteroids. Politically, we may fail to act in time. Bureaucracy, mistrust, denial, all could doom us long before the rock arrives. Psychologists call this normalcy bias, the tendency to assume tomorrow will look like today. It makes people underestimate rare disasters. It's why residents ignore evacuation orders before hurricanes, or why financial markets ignore warning signs before crashes. It's also why governments may hesitate to fund planetary defense. An asteroid strike hasn't happened in living memory, so the danger feels abstract. Apophis cracks that bias. It reminds us that the danger is real, even if the outcome is benign. When millions of people see it with their own eyes, brighter than many stars, sliding past Earth closer than satellites, denial will no longer feel safe. The chaos god will demand an answer: are we prepared, or are we pretending? Some visionaries have suggested a dedicated international agency, something like a planetary defense council, with authority to act on behalf of Earth. It would combine funding, expertise, and decision-making power, bypassing the slow grind of national politics. But so far, that remains only an idea. Nations guard their sovereignty too tightly. For now, planetary defense is piecemeal, NASA testing impactors, ESA planning follow-up missions, the UN coordinating conversations. The real test will come when the clock is ticking. If astronomers announce an impact probability above 50% for a rock like Apophis, will nations rise above mistrust? Or will they bicker while the countdown ticks away? History offers both caution and hope. During the Cold War, rivals who distrusted each other profoundly still cooperated on the International Space Station. Shared survival created shared incentives. Perhaps an asteroid threat would do the same. Perhaps the chaos god, instead of dividing, would unite. But unity will not happen automatically. It must be prepared. Agreements must be written before crisis strikes. Protocols must be tested. Simulations must be run. Otherwise, when the warning comes, we'll be improvising with the clock already ticking. That is why every flyby matters. Every survey matters. Every conversation matters. Apophis is not just a rock. It's a mirror, showing us how fragile our systems are, how easily politics could fail us. The rock doesn't care whether we cooperate. The question is whether we care enough to do it anyway. And here's the deeper irony. If humanity ever does unite around planetary defense, it may be the first truly global project. Not colonizing Mars, not fighting wars, not competing for resources, but saving the one planet we already have. The Chaos God could be the catalyst for our greatest act of unity. But unity requires vision. And vision requires imagination. That's why storytelling matters. That's why scientists write papers, but also why filmmakers, writers, and educators tell stories about asteroids. Not to scare, but to help us imagine. Because until we can imagine the fireball, the crater, the famine, the choice, we won't act. Apophis gives us that chance to imagine. A near miss so close it will shine overhead, reminding us that the sky is not empty. That probability is not zero. That decisions matter. And so, the next phase of our journey takes us from politics to culture. Because when the chaos god streaks across the sky, it won't just be astronomers and presidents who react. It will be everyone. Artists. Writers. Children. Farmers. Workers. The entire human family, looking up together. And how we tell the story of that night may shape how we respond when the next warning comes. Long before telescopes, long before physics, humans looked at the night sky and told stories. Stars became hunters, bears, serpents, and gods. Comets were omens, warnings from the heavens. Meteors were messages, streaks of fire sent by unseen forces. For most of history, the cosmos wasn't just rocks and gas, it was meaning. That instinct hasn't left us. Even now, with orbital mechanics in hand, we still wrap asteroids in myth. And Apophis, the chaos god, is the perfect example. In Egyptian mythology, Apophis, or Apep, was the great serpent of chaos. Every night, he attacked the sun god Ra as Ra sailed his bark across the underworld. Every dawn was a victory, proof that order had triumphed once again. But the battle never ended. Apophis always returned, a serpent lurking in the dark, waiting to swallow the light. When astronomers named asteroid 99942 Apophis in 2005, it wasn't just poetic. It was fitting. A rock from the darkness, threatening to bring chaos, destined to return again and again until chance, or fate, decided the outcome. Science gave it an orbit. Myth gave it a story. And that story spread. Headlines wrote of the chaos god asteroid. Blogs speculated about omens. Preachers worked it into sermons. Internet forums wove it into conspiracies. For a time, Apophis wasn't just a rock. It was a symbol, a mirror reflecting our deepest fears. Because asteroids are uniquely powerful symbols. They embody randomness. They don't come with warnings. They don't follow human logic. They remind us that no matter how powerful our civilizations become, we are still fragile animals living under an open sky. That fragility breeds myth. Consider comets. In ancient Rome, comets were seen as harbingers of doom, often tied to the deaths of emperors. In medieval Europe, they were linked to plagues and wars. Even Halley's Comet, when it returned in 1910, sparked panic. Some believed its tail would poison the Earth with cyanogen gas. Newspapers sold anti-comet pills to the fearful. The cosmos had become a story of dread. Asteroids have inherited that mantle. Tunguska was remembered in Siberian folklore as a fiery curse. Chelyabinsk became the subject of viral videos and memes. And Apophis, thanks to its name, its date, and its near miss, has already taken root in modern myth. But myths are not just about fear. They're about meaning. The Egyptians didn't despair at Apophis. They built rituals to fight him. Priests recited spells to bind the serpent, to help Ra win the nightly battle. It was chaos, yes, but chaos that could be resisted. In that sense, Apophis the asteroid carries the same dual meaning. It is chaos, but it also offers us the chance to fight. To act. To prove that this time, humanity is Ra, not prey. Popular culture has seized on this. Movies, documentaries, novels, they all mine asteroid threats for drama. Why? Because the metaphor is irresistible. A rock in the sky becomes a stand-in for mortality, for fate, for the fragile line between survival and extinction. In a single image, a fireball streaking toward Earth, you can capture the fear of annihilation, the hope of salvation, the test of courage. But here's the twist. Unlike other myths, this one is true. Asteroids really do threaten us. They have before, they will again. The metaphor is not metaphor at all. It is reality. And that makes Apophis different from any serpent in ancient stories. Its fangs are measurable. Its orbit is calculable. Its chaos is real. That reality has bled into public imagination. In forums and social media, Apophis is sometimes cast as prophecy, a sign of judgment. In video games, it becomes a level boss, a monster to be defeated. In documentaries, it's framed as a wake-up call. Across cultures, the story is retold in different voices, but always with the same core, chaos from above. And there's a strange power in that. Because myth shapes action. People fund what they fear. Politicians respond to stories, not just statistics. When Apophis streaks across the sky in 2029, brighter than most stars, millions will feel something primal. Not just curiosity, but awe. Not just awe, but dread. And that dread may drive action in ways that dry probabilities never could. We've seen this before. Chelyabinsk, caught on dashboard cameras, didn't just injure people. It galvanized funding. It reminded governments that space rocks aren't ancient history, they're present tense. In the same way, Apophis could ignite a cultural shift. From myth to mobilization. From stories to strategies. But myths can cut both ways. If framed as prophecy, Apophis could fuel fatalism, it's fate, we can't fight it. If framed as spectacle, it could be trivialized, what a pretty light show. The challenge is to frame it as responsibility, this is real, but we can act. That framing, more than any telescope or rocket, may determine whether humanity takes planetary defense seriously. In a sense, Apophis is already shaping culture. Musicians write songs about it. Artists paint it. Writers imagine futures where it strikes or misses. It has joined the pantheon of cosmic symbols, alongside black holes and supernovas. It is no longer just a number in a catalog. It is a story we tell ourselves. And maybe that's the most important part. Because stories move us in ways numbers cannot. The probability of impact is abstract. But the image of a serpent in the sky, that lingers. That inspires. That terrifies. That motivates. So when Apophis passes in 2029, the real spectacle may not be in the sky. It may be in us. In how we interpret it. In how we tell the story to our children. In how we weave chaos into meaning. Because Apophis is more than an asteroid. It's a reminder of our place in the cosmos, small, fragile, but not powerless. Chaos circles us, but like RA, we can fight. We can plan. We can build. And in doing so, we might find that the myth becomes true, not a story of doom, but a story of survival. But to survive, we need more than myths. We need science, yes. Politics, yes. But also economics. Because saving Earth will not be cheap. And in a world of limited budgets, planetary defense must compete with every other human priority. Which brings us to the next question: what is survival worth? Asteroids don't care about money. They don't send invoices or balance sheets. They just move, silently, according to physics. But if humanity wants to do something about them, the conversation quickly turns to budgets. Because planetary defense, like every other human endeavor, is bound by economics. So how much does it cost to protect the planet? Surprisingly little. Or shockingly much. It depends on how you frame it. Let's start with the numbers. NASA's Planetary Defense Coordination Office, established in 2016, runs on about $150 million a year. That may sound like a lot, until you realize it's less than 1% of NASA's overall budget, and a microscopic fraction of US government spending. For comparison, the US military spends more than that every hour. Global advertising expenditures dwarf it many times over. Humanity spends more each year on ice cream than on asteroid defense. That mismatch reveals something profound: we don't yet treat planetary defense as urgent. Because if we did, the funding would be orders of magnitude higher. The NEO Surveyor mission alone, a space telescope designed to find the asteroids we're still missing, has an estimated cost of about $1.2 billion. That's the price of a sports stadium. A single stadium, versus a mission that could save millions of lives. Yet even that budget has faced delays and cuts. Why? Because politicians deal in cycles of years. Planetary defense deals in cycles of decades and centuries. The timelines don't align. Spending billions to prevent a disaster that might not occur for 50 years is a hard sell to voters. The result is chronic underfunding, even as the danger remains. But here's the irony: prevention is far cheaper than recovery. If a 300-meter asteroid like Apophis were to strike, the economic damage could reach into the trillions. Entire cities wiped out. Croplands ruined. Ports and power grids destroyed. Insurance markets collapsing. Global trade disrupted. Recovery would dwarf the cost of a few billion spent on detection and deflection. By orders of magnitude. Think of it like earthquake retrofitting. Reinforcing a building costs money up front. But when the quake hits, that investment pays off in lives saved and cities preserved. Planetary defense is the same principle, except the building is Earth, and the quake comes from the sky. Some economists have tried to put numbers to it. One analysis suggested that every dollar spent on asteroid detection yields $10 to $50 in avoided damages over the long run. In pure economic terms, planetary defense is one of the best bargains available. Yet still, funding remains meager. Why? Because people underestimate low probability, high impact risks. Insurance against rare events feels wasteful, until the event happens. The Chelyabinsk meteor in 2013 offered a glimpse of the cost of unpreparedness. The blast injured 1,500 people and caused about $30 million in damage, mostly from shattered windows. And that was from a rock only 20 meters wide. Scale that up to Apophis, 340 meters, and the costs multiply exponentially. Now you're not replacing windows. You're rebuilding entire cities. You're resettling millions. You're navigating a global food crisis triggered by dust in the atmosphere. No insurance policy could cover that. Only prevention could. But prevention itself has costs beyond money. Building survey telescopes requires time. Launching missions requires rockets, fuel, technology, and international cooperation. Planetary defense competes with other urgent needs: poverty relief, climate change, healthcare. Politicians ask, why spend billions on a threat that might never materialize, when crises on Earth are immediate and visible? The answer lies in perspective. Planetary defense isn't an alternative to solving earthly problems. It's a foundation. Civilization exists only as long as Earth is safe enough to sustain it. If we ignore cosmic threats, all our other investments, hospitals, schools, climate initiatives, could be undone in seconds by a single strike. Insurance is never glamorous, but it is essential. Some advocates argue for reframing. Instead of presenting planetary defense as asteroid insurance, present it as opportunity. Every dollar spent on surveys funds jobs for astronomers and engineers. Every spacecraft built for deflection tests advances propulsion, navigation, and robotics technologies. The same telescopes that find asteroids can also spot supernovae, exoplanets, and comets. The money doesn't vanish, it builds infrastructure and knowledge. It strengthens humanity in ways beyond survival. There's also the question of shared cost. Should the burden fall on wealthy nations? On those with space programs? On the UN? The truth is, everyone has a stake. Asteroids don't aim at borders. An impact in Africa could ruin harvests in Asia. A strike in the Pacific could drown US cities. The ripple effects are global. That means funding should be global too. Imagine if each nation contributed a fraction of a percent of its GDP toward a planetary defense fund. The total would be more than enough to build telescopes, launch missions, and sustain vigilance indefinitely. But cooperation, as we've seen, is easier said than done. Here's where Apophis could tip the scales. In 2029, when billions watch it streak across the sky, politicians will face questions. What if it had hit? What about the next one? What are we doing to prepare? That cultural moment could unlock funding in a way spreadsheets never could. Fear and awe, combined with visibility, may finally force budgets to align with reality. Because the economics of planetary defense aren't just about numbers. They're about values. What is survival worth? What is peace of mind worth? Is a few $1 billion too high a price to protect the only habitable planet we know? The answer seems obvious. Yet history shows we often wait until after disaster to invest. Fire codes follow fires. Levees follow floods. Seatbelts follow crashes. Must asteroid defense follow impact? Or will Apophis be the rare case where we act before, not after? That choice will define more than budgets. It will define whether we learn from warnings or ignore them. Because the chaos god is circling, and survival is not just about science. It's about whether we value tomorrow enough to pay for it today. And that brings us to the future. Because planetary defense isn't just about one asteroid. It's about building a long-term strategy for survival in a solar system full of wandering rocks. Which leads to the next chapter, how the 2029 flyby could shape not only science and politics, but the future trajectory of human civilization itself. April 13, 2029. A date already etched into history, not because disaster will strike, but because it won't. That night, Apophis will thread the cosmic needle, sliding past Earth closer than our satellites, visible to the naked eye. For the first time, humanity will watch a rock the size of a mountain skim by in real time. For the first time, survival will feel like a spectacle. But what comes after? Apophis won't just be a flyby. It will be a pivot. A cultural hinge. A scientific turning point. A moment that may define how humanity approaches the next century of life in the cosmos. Consider first the science. Apophis is not just another asteroid. It's a natural experiment on a grand scale. Earth's gravity will tug on it, distort it, maybe even shake loose boulders from its surface. Telescopes will watch. Spacecraft will measure. OSIRIS-APEX will orbit, recording before and after changes with exquisite precision. The data will transform our understanding of rubble pile asteroids, orbital mechanics, and tidal stresses. Those lessons will ripple forward, guiding every future deflection mission. In short, Apophis will turn asteroid science from theory into practice. Models will be tested. Assumptions will be challenged. For the first time, we'll see how a potentially hazardous asteroid behaves when passing dangerously close. That knowledge will arm us against the next threat. But science is only part of the story. Culture matters too. Billions of people will look up and see Apophis. In cities across Europe, Africa, and Asia, it will shine brighter than most stars, moving visibly across the sky in minutes. It will be on live streams, on headlines, on social media feeds. Children will remember the night they saw the chaos god pass by. That shared experience could leave a mark as deep as the moon landing. The Apollo missions redefined space exploration by proving humans could walk on another world. Apophis could redefine planetary defense by proving rocks can miss, and by reminding us they might not always. That memory may fuel a generation of scientists, engineers, and leaders to take the threat seriously. To fund telescopes. To test tractors. To prepare. And preparation leads naturally to technology. If Apophis inspires new missions, new budgets, new urgency, the ripple effects could accelerate advances in propulsion, robotics, and space-based infrastructure. The same engines that could push deflection spacecraft could power exploration to Mars. The same telescopes that find asteroids could discover exoplanets. Planetary defense isn't a distraction from space exploration. It's a foundation for it. Protect Earth first, then reach outward. There's also the question of mining. Apophis, like many asteroids, is made of silicate rock mixed with nickel and iron. Some asteroids carry rare metals, even platinum and gold. If humanity learns how to rendezvous, study, and deflect them, we'll also learn how to harvest them. Planetary defense and asteroid mining share the same technologies: propulsion, capture, resource processing. In a strange way, saving Earth and exploiting space may be two sides of the same coin. But the deepest impact of Apophis may be philosophical. For centuries, humans have treated Earth as a closed system, threatened only by ourselves. Wars, plagues, climate, our dangers came from within. Apophis reminds us that the universe itself is a player. That extinction doesn't care about borders or politics. That we are one species on one planet under one sky. That realization could reshape how we think of ourselves. The overview effect, the psychological shift astronauts feel when seeing Earth from orbit, may be scaled up. Billions of people, looking up together, may feel a similar shift. A sense that survival is shared. That the sky unites more than it divides. If that feeling sticks, it could be the beginning of something bigger, a planetary identity. Of course, that's the optimistic view. The pessimistic view is that Apophis comes and goes, headlines flare and fade, and the world forgets. That we marvel, then move on. That budgets stay small, telescopes stay few, and the chaos god's warning is ignored. Which future will we choose? History suggests both paths are possible. The moon landing inspired decades of exploration but was followed by decades of retreat. Climate warnings sparked action but also denial. Chelyabinsk jolted us awake, only for apathy to creep back. Will Apophis be remembered as a turning point, or a missed opportunity? The answer depends on what we do in the years after. If NEO Surveyor launches. If OSIRIS-APEX succeeds. If international treaties on planetary defense are written. If budgets grow. If public memory holds. Then 2029 could mark the birth of a new era, the century when humanity finally accepted its place in a dangerous universe and chose foresight. If not, then Apophis will fade into memory, another close call, another myth, another serpent slipping back into the dark. But here's the key, the future is not written. Not yet. It is in our hands, as much as in Apophis's orbit. And that orbit, after 2029, will carry the rock back out into the solar system, only to return again decades later. Each pass will remind us that chaos is patient, and survival is not guaranteed. In a way, Apophis is not just a rock. It's a clock. A ticking reminder that the universe plays by probabilities, not promises. That close calls are warnings, not guarantees of safety. That time is a resource, and one day, time will run out. The question is whether we'll use that time wisely. And that brings us to the next part of our story, the timeline. Because planetary defense isn't just about 2029. It's about the decades that follow. The keyholes. The resonances. The centuries of orbits that may or may not line up with Earth's. To understand the long-term future, we must map the chaos itself. Because only by reading the clock can we know how much time we really have. April 13, 2029. A date already etched into history, not because disaster will strike, but because it won't. That night, Apophis will thread the cosmic needle, sliding past Earth closer than our satellites, visible to the naked eye. For the first time, humanity will watch a rock the size of a mountain skim by in real time. For the first time, survival will feel like a spectacle. But what comes after? Apophis won't just be a flyby. It will be a pivot. A cultural hinge. A scientific turning point. A moment that may define how humanity approaches the next century of life in the cosmos. Consider first the science. Apophis is not just another asteroid. It's a natural experiment on a grand scale. Earth's gravity will tug on it, distort it, maybe even shake loose boulders from its surface. Telescopes will watch. Spacecraft will measure. Osiris Apex will orbit, recording before and after changes with exquisite precision. The data will transform our understanding of rubble pile asteroids, orbital mechanics, and tidal stresses. Those lessons will ripple forward, guiding every future deflection mission. In short, Apophis will turn asteroid science from theory into practice. Models will be tested. Assumptions will be challenged. For the first time, we'll see how a potentially hazardous asteroid behaves when passing dangerously close. That knowledge will arm us against the next threat. But science is only part of the story. Culture matters too. Billions of people will look up and see Apophis. In cities across Europe, Africa, and Asia, it will shine brighter than most stars, moving visibly across the sky in minutes. It will be on live streams, on headlines, on social media feeds. Children will remember the night they saw the chaos god pass by. That shared experience could leave a mark as deep as the moon landing. The Apollo missions redefined space exploration by proving humans could walk on another world. Apophis could redefine planetary defense by proving rocks can miss, and by reminding us they might not always. That memory may fuel a generation of scientists, engineers, and leaders to take the threat seriously. To fund telescopes. To test tractors. To prepare. And preparation leads naturally to technology. If Apophis inspires new missions, new budgets, new urgency, the ripple effects could accelerate advances in propulsion, robotics, and space-based infrastructure. The same engines that could push deflection spacecraft could power exploration to Mars. The same telescopes that find asteroids could discover exoplanets. Planetary defense isn't a distraction from space exploration. It's a foundation for it. Protect Earth first, then reach outward. There's also the question of mining. Apophis, like many asteroids, is made of silicate rock mixed with nickel and iron. Some asteroids carry rare metals, even platinum and gold. If humanity learns how to rendezvous, study, and deflect them, we'll also learn how to harvest them. Planetary defense and asteroid mining share the same technologies: propulsion, capture, resource processing. In a strange way, saving Earth and exploiting space may be two sides of the same coin. But the deepest impact of Apophis may be philosophical. For centuries, humans have treated Earth as a closed system, threatened only by ourselves. Wars, plagues, climate, our dangers came from within. Apophis reminds us that the universe itself is a player. That extinction doesn't care about borders or politics. That we are one species on one planet under one sky. That realization could reshape how we think of ourselves. The overview effect, the psychological shift astronauts feel when seeing Earth from orbit, may be scaled up. Billions of people, looking up together, may feel a similar shift. A sense that survival is shared. That the sky unites more than it divides. If that feeling sticks, it could be the beginning of something bigger, a planetary identity. Of course, that's the optimistic view. The pessimistic view is that Apophis comes and goes, headlines flare and fade, and the world forgets. That we marvel, then move on. That budgets stay small, telescopes stay few, and the chaos god's warning is ignored. Which future will we choose? History suggests both paths are possible. The moon landing inspired decades of exploration but was followed by decades of retreat. Climate warning sparked action but also denial. Chelyabinsk jolted us awake, only for apathy to creep back. Will Apophis be remembered as a turning point, or a missed opportunity? The answer depends on what we do in the years after. If NEO Surveyor launches. If Osiris Apex succeeds. If international treaties on planetary defense are written. If budgets grow. If public memory holds. Then 2029 could mark the birth of a new era, the century when humanity finally accepted its place in a dangerous universe and chose foresight. If not, then Apophis will fade into memory, another close call, another myth, another serpent slipping back into the dark. But here's the key, the future is not written. Not yet. It is in our hands, as much as in Apophis's orbit. And that orbit, after 2029, will carry the rock back out into the solar system, only to return again decades later. Each pass will remind us that chaos is patient, and survival is not guaranteed. In a way, Apophis is not just a rock. It's a clock. A ticking reminder that the universe plays by probabilities, not promises. That close calls are warnings, not guarantees of safety. That time is a resource, and one day, time will run out. The question is whether we'll use that time wisely. And that brings us to the next part of our story, the timeline. Because planetary defense isn't just about 2029. It's about the decades that follow. The keyholes. The resonances. The centuries of orbits that may or may not line up with Earth's. To understand the long-term future, we must map the chaos itself. Because only by reading the clock can we know how much time we really have. April 13, 2029, will come and go. Apophis will skim past Earth, dazzling billions, and vanish again into the dark. Cities will cheer, live streams will spike, telescopes will hum. Then the headlines will fade. Life will return to its rhythm. But something fundamental will remain, a memory. The night the chaos god passed us by. And memory matters. Because Apophis is not just an asteroid. It's a story. A mirror. A teacher. Science tells us it is a 340-meter stony rock, orbiting the Sun every 323 days. A rubble pile or a monolith, held together by weak gravity. A dot tracked by radar, mapped by mathematics, safe for a century. That's the scientific truth. But science alone is not enough. Myth gives Apophis meaning. The serpent of chaos. The eternal foe of RA. The reminder that order must be fought for, never assumed. That every dawn is victory, but never permanence. When we look at Apophis, we see not only a rock, but our fears made manifest, randomness, fragility, mortality. Culture amplifies it. Movies dramatize it. News headlines sensationalize it. Social media spins it into prophecy or parody. Children will grow up remembering the night it passed, some inspired, some frightened, some simply awed. Like comets in the past, Apophis will leave a cultural scar as much as a scientific one. Politics complicates it. Who decides what to do if the next Apophis aims true? Who funds the missions? Who commands the rockets? Who takes responsibility for failure? Planetary defense isn't just engineering. It's governance. And our record there is shaky. Nations quarrel. Budgets stall. Denial whispers. The chaos god tests not just our telescopes, but our ability to cooperate. Economics pressures it. Planetary defense is cheap compared to war, compared to rebuilding after hurricanes, compared to the cost of a single major city lost. But it is still expensive. Still a line item to be debated. Still competing with immediate crises. The paradox is cruel. Prevention looks costly until the cost of inaction is revealed. By then, it's too late. Psychology frames it. People fear the immediate, not the distant. They panic when told, certain impact, but shrug at 2% chance. They either deny or despair. Rarely do they prepare. Apophis exposes that flaw in our nature. The flaw that could doom us if we wait too long. And yet, hope runs through it all. Because Apophis is not impact. It is mercy. A close call, not a catastrophe. A rehearsal, not a funeral. A chance to see, to learn, to prepare. A serpent we can face in safety, before the day comes when the serpent bites. Think about the tools we've built already. DART, a vending machine-sized spacecraft, changed the orbit of a moonlet 11 million kilometers away. OSIRIS-RX returned samples from Bennu and will meet Apophis after its flyby. NEO Surveyor will scan the heavens in infrared, finding thousands of hidden rocks. The gravity tractor waits as a subtle option. Even nuclear devices sit, grim but ready, in the toolbox. Humanity has begun to arm itself, not with fear, but with foresight. Apophis crystallizes why that matters. Not because it will strike, but because it could have. And because one day, one of its cousins will. The dice of the cosmos roll endlessly. The scars on Earth, the craters, the blast zones, the shattered forests, prove it. Chicxulub ended the dinosaurs. Tunguska flattened a wilderness. Chelyabinsk cracked a modern city. These were warnings written in fire. Warnings we would be fools to ignore. And so, the real story of Apophis isn't whether it hits. It's whether we listen. Whether we take the gift of time and turn it into preparation. Whether we let awe become action. Whether we let myth become motivation. Whether we, fragile and flawed, choose to be RA in the bark of the sun, fighting chaos with foresight, instead of prey waiting for impact. When you look up in 2029, and see the serpent in the sky, remember, this is not just a show. It is a test. A reminder of what's at stake. A rehearsal for the day probability turns into certainty. And that rehearsal belongs to all of us. To scientists scanning the skies. To politicians setting budgets. To storytellers shaping culture. To ordinary people, watching, asking, demanding action. Because planetary defense is not abstract. It is not for someone else. It is for everyone who breathes air and walks this earth. So here is the final cliffhanger: what happens after the chaos god passes? Do we learn, unite, and prepare? Or do we marvel, forget, and wait for the next rock? The choice is ours. The clock is ticking. The serpent circles still. And if you've stayed with this journey, ask yourself, what role do you play in this story? Would you support funding planetary defense? Would you spread awareness? Would you teach others why Apophis matters? Leave your thoughts in the comments. Share this story with someone who doesn't yet know. Because the chaos god is real, and so is our chance to face him. The most interesting stuff is still to come. Stay tuned.